There is a particular kind of darkness that settles in after midnight, when the world has gone quiet and the last sounds of the day have finally faded into silence. You know this darkness. You have felt it before. It is the kind of darkness that does not feel empty, but full of something you cannot quite name, something that breathes just beyond the edges of your vision, something that waits with the patience of an ancient thing that has never needed to hurry. And on certain nights, when the sky is clear and the clouds have pulled themselves away like curtains drawn back from a stage, you can look upward and you can see them. The stars. They are always there, of course. They do not leave. They do not rest. They burn and burn and burn across distances so vast that the numbers used to describe them lose all meaning the moment they are spoken aloud. And yet, on a night like this, a night that feels thick with mystery, a night that seems to lean in close as though it wants to whisper something, the stars do not look like points of fire. They look like eyes. Not the warm eyes of something familiar, not the eyes of something that means you well, but old eyes, cold eyes, eyes that have witnessed things that no living creature was ever meant to see, things that happened before the first molecule of life ever arranged itself on this small and fragile planet, things that are still happening now, right now, in the silent and lightless spaces between worlds. Tonight, we are going to talk about those things. We are going to talk about what happens when a star dies. And more importantly, we are going to talk about what happens when a star dies, but does not quite finish the job. We are going to talk about the ones that linger. We are going to talk about the ones that linger, the ones that should be gone, the ones that every law of physics and every model of stellar evolution says cannot still exist. And yet, there they are, drifting through the galaxy like something out of a fever dream, like something that has crawled back from a place that has no name, charred and broken and glowing with a light that should not be. We call them zombie stars. And before you let that phrase settle too comfortably into the familiar category of science fiction, before your mind reaches for a story you already know, let me tell you something. These are not metaphors. They are not poetic inventions. They are real. They have been found. There is one, right now, moving through our galaxy, a battered and mutilated core of something that was supposed to have been completely destroyed, drifting through space at a speed so extraordinary that astronomers could not believe their instruments when they first measured it. But we will get to that. For now, let the darkness settle around you. Let the weight of the night press gently against your skin. Take a slow breath, and then another, and let the ordinary world, the world of daylight and sound and certainty, let it fall away just a little. Because the story we are about to tell requires a certain kind of openness, a willingness to sit with things that are strange and vast, and deeply uncomfortable in the most beautiful possible way. The universe is not a gentle place. It is not designed with comfort in mind. It operates according to rules that were written before there were any minds to read them, and those rules are indifferent to the preferences of the creatures that eventually emerge to study them. Stars are born in violent clouds of collapsing gas. They live by the sustained force of nuclear fire, and they die in explosions so catastrophic that for a brief moment, a single dying star can outshine an entire galaxy containing hundreds of billions of other suns. This is the universe we live in. This is the sky above you tonight. And somewhere out there, in the dark spaces between the stars you can see, there are other stars. Stars that cannot be seen with the naked eye. Stars that drift without purpose through the void, scarred and smoldering, neither fully alive nor fully dead. Stars that experience something so violent, so cosmically catastrophic, that they should not exist at all. And yet they do. The universe, it turns out, does not always follow its own rules. There is something deeply gothic about that realization, something that belongs to the same category of feeling as an old house on a hill, a door that opens by itself, a reflection in a mirror that moves a half-second too late. The universe has its versions of these things, and zombie stars are among the most haunting of them all. So settle in. Let your breathing slow. Let your muscles release the tension they have been holding all day. And let the night do what the night has always done best, which is to open a door into the parts of reality that the bright light of day tends to keep hidden. This is the story of stars that refuse to die. And it begins, as all the best stories do, with fire. Take one more slow breath. Feel the darkness around you. And let us begin. Before we can understand what it means for a star to die, and before we can begin to approach the strangeness of a star that dies but does not stay dead, we need to spend some time with what a star actually is. Not the shorthand version, not the simple answer, but the real thing, the physical truth of it, the version that, when you sit with it long enough, starts to feel less like a scientific fact and more like a kind of magic that has simply been given a technical name. A star is, at its most fundamental, a battle. It is a battle between two forces that are, in a sense, completely opposed to each other. One of those forces wants to crush everything inward. The other wants to push everything outward. And a star is what happens when those two forces reach an agreement, a temporary, fragile, fiery agreement, and hold each other in a kind of suspended tension for millions or billions of years. The force that wants to crush everything inward is gravity. You already know gravity. You feel it every moment of your life. It pulls you toward the floor, toward the earth, toward the center of this planet. But the gravity you experience in your daily life is a whisper compared to what gravity becomes when you gather enough mass in one place. When you take an enormous cloud of hydrogen gas, a cloud that might be dozens of light years across, and you begin to let it collapse under its own weight, gravity becomes something monstrous, something relentless, something that tightens and tightens and tightens with no mercy and no pause. At the center of a collapsing cloud of gas, as the pressure builds and the temperature rises, something extraordinary happens. The hydrogen atoms, the simplest atoms in the universe, begin to move faster and faster as the temperature climbs. They collide with more and more force. And eventually, under conditions of heat and pressure so extreme that the numbers describing them are almost meaningless in human terms, something happens that changes everything. Two hydrogen nuclei fuse together. They combine. They become something new, something heavier, and in the process of doing so, they release a tiny, almost unimaginably small quantity of energy. But then two more hydrogen nuclei fuse, and then two more, and then two more. And within the core of this collapsing cloud, this process ignites, not gradually, not gently, but all at once, like a fire catching in a room full of dry wood, and suddenly, there is a star. The energy released by this fusion pushes outward. It pushes against the gravity that is still trying to crush everything inward. And when the outward push of nuclear fire exactly balances the inward pull of gravity, the star finds its equilibrium. It stops collapsing. It does not explode. It simply burns, steadily and brilliantly, radiating light and heat in every direction. A sphere of sustained nuclear fire suspended in the darkness of space. This is a star, a negotiation between destruction and creation, held in place for as long as the fuel lasts. And the fuel does last, for a remarkably long time. Our own sun has been burning for approximately 4.5 billion years, and it has enough hydrogen left to continue burning for another 5 billion years or so. For a star of the sun's size and type, the total lifespan is around 10 billion years. A number so large that it almost feels like permanence, almost feels like forever, but it is not forever. Nothing in the universe is forever, and the way a star ends depends enormously on how large it is when it begins. A star like our sun, a middle-sized star, a thoroughly ordinary star by cosmic standards, will burn through its hydrogen in the core over billions of years. As the hydrogen in the center is used up, the core begins to contract again under gravity while the outer layers of the star expand outward, puffing up into what astronomers call a red giant. The star grows enormous, swelling to hundreds of times its original size. Eventually, the outer layers are shed entirely, drifting away into space as a beautiful, glowing cloud of gas called a planetary nebula. And what is left behind is something we will return to many times tonight. The core, the dense, hot, compressed heart of what was once a fully burning star, now stripped of its outer layers, now no longer capable of sustaining fusion. It is left alone in space to slowly cool. This remnant is called a white dwarf, and it is, in many ways, the beginning of our story rather than the end. But before we go there, let us spend a moment more with the larger stars, the ones that are not ordinary, the ones that are massive, truly massive, 10 or 20 or 50 times the mass of our sun. These stars burn faster and hotter and brighter. They go through their fuel with a kind of reckless speed, as though they know they do not have long and have decided to spend everything they have all at once. A very massive star might live for only a few million years, a fleeting moment by cosmic standards. And when it reaches the end of its fuel, it does not go quietly. It does not gently shed its outer layers and leave a cooling ember behind. It collapses. All at once, catastrophically, the core of the star falls in on itself in a fraction of a second, and the energy released by that collapse is so enormous, so staggeringly violent, that it sends the outer layers of the star flying outward in an explosion that, for a brief time, can outshine the entire galaxy. This is a supernova. This is a supernova, and it is, by almost any measure, the most spectacular event that the universe regularly produces. The word supernova might be familiar to you. It is one of those words that has escaped the world of science and entered the general vocabulary, but familiarity can sometimes be the enemy of true understanding. Let the word settle again, as though you are hearing it for the first time. A supernova, a single star, dying, releasing in its final moments more energy than our sun will release over its entire 10 billion year lifetime. A blast so bright that it can be seen from other galaxies. A death so complete, so total, so absolute, that nothing of the star itself survives in any recognizable form. Or so we thought. We will come back to that. We will come back to what happens when the explosion is not quite complete, when the death is not quite absolute, when something is left behind that should not be left behind. But first, let us sit a little longer with the quieter death. The gentler ending, the one that leaves behind something small and dense and cooling in the dark. The white dwarf, because that is where our Gothic story truly begins to take shape. Not in the violence of a supernova, but in the long, slow, quiet death of an ordinary star. In the lingering presence of a cooling ember. In the way the darkness surrounds it, and the way it dims, degree by degree, year by year, millennium by millennium. There is something deeply unsettling about a white dwarf when you think about it long enough. It is not quite alive because it is not producing energy through fusion anymore, and it is not quite dead because it is still radiating light, still glowing with the stored heat of a lifetime of nuclear burning. It exists in a strange middle space. It exists in a strange middle space, an in-between state, a threshold between fire and darkness. And it is precisely this in-between quality that makes it vulnerable. It is precisely this state of being neither fully alive nor fully dead that opens the door to the events we are going to describe tonight. So let the image settle. A white dwarf floating in space, dense and hot and gradually cooling, alone in the dark. The fire that sustained it for billions of years is gone, but the heat of that fire has not yet fully faded. It is a star in the process of becoming something else. And sometimes, in the process of becoming something else, something intervenes. Something approaches. Something close. Something with gravity of its own. And the story begins to turn dark. Every culture that has ever looked up at the night sky has told stories about the stars. The Greeks saw heroes and monsters. The Egyptians saw the souls of the dead. The ancient peoples of the Pacific saw navigation charts written in light, paths across the water, guidance for those brave enough to follow them into the open ocean. Across every culture, across every age of human history, the stars have been interpreted as meaningful, as intentional, as part of a story that has something to say to those below. But there is one story that none of those ancient sky watchers ever told. Because it is not the kind of story that reveals itself to the naked eye. It is not written in the positions of the stars or in the patterns they make on the horizon at sunrise. It is written in a language that took centuries of science to learn to read. And it is, in many ways, the most disturbing story the sky has to tell. It is the story of what the stars are actually doing. Not the metaphor of them. Not the metaphor of them. Not the mythology. But the physical reality. The ongoing, ceaseless, utterly indifferent process of nuclear burning and gravitational collapse that every single star in the universe is engaged in at every single moment of its existence. What the stars are doing, all of them, without exception, is dying. Not quickly, not on any timescale that a human life could register. But the process of stellar death begins at the same moment as the process of stellar birth. The moment a star ignites, the moment that first fusion reaction releases its first photon of light, the clock begins. The fuel is finite, the burning is constant, and the ending is inevitable. There is something that feels very gothic about this truth. The idea that the light you see, the light that has traveled for years or centuries or millennia to reach your eyes on this particular night, is the product of a slow destruction. That the beauty of a starry sky is inseparable from the ongoing process of annihilation that produces it. That every point of light above you tonight is a thing that is consuming itself, and that the consumption will eventually be complete. This is the promise of destruction that is built into every star, and it is a promise that the universe always keeps. The details of how that promise is fulfilled depend, as we touched on briefly, on the mass of the star. And mass, in the world of stellar physics, is everything. It determines how hot the star burns, how long it lives, how bright it shines, and how violently or quietly it dies. Mass is the single most important characteristic of a star, the variable from which almost everything else follows. For the smaller stars, the ones like our Sun and below, the death is quiet by cosmic standards. The hydrogen in the core is exhausted over billions of years. And iron is where the story breaks. Iron is the end of the line for stellar fusion. Iron cannot be fused to release energy. In fact, fusing iron requires energy rather than releasing it. So when the core of a massive star accumulates enough iron, the nuclear burning stops. The outward pressure that has been holding gravity at bay for millions of years vanishes. And gravity, which has been waiting with infinite patience, finally wins. The core of the star collapses. In a fraction of a second, a fraction so small it barely deserves to be called a unit of time, the core implodes. It goes from being a sphere roughly the size of Earth to being a sphere roughly the size of a city. The density it reaches is incomprehensible. The atoms themselves are crushed, electrons forced into protons, protons becoming neutrons, the entire core transformed into a single enormous atomic nucleus, trillions of tons of matter compressed into a space of only a few kilometers. And the energy released by this collapse, The gravitational potential energy of all that falling mass is enormous beyond almost any comparison. The collapsing core bounces. The shockwave from that bounce travels outward through the star at a significant fraction of the speed of light. And when it reaches the outer layers, it does not merely dislodge them. It annihilates them. It flings them outward with such violence that they reach speeds of tens of thousands of kilometers per second. The star, in the span of a moment that contains more energy than most minds can hold, destroys itself. This is the supernova. This is the promised destruction fulfilled in the most absolute way the universe knows how to fulfill a promise. The brightness of a core collapsed supernova at its peak can rival an entire galaxy. A single dying star, outshining 200 billion other stars combined. For a brief period, ranging from days to weeks, this explosion blazes across space, visible to observers in other galaxies, a lighthouse of annihilation marking the spot where something once stood. And then it fades. The light diminishes. The expanding shell of debris drifts outward into space. And what is left behind, if anything survives the collapse, is either a neutron star, a sphere of densely packed neutrons spinning rapidly and emitting beams of radiation, or a black hole, a point of gravity so intense that not even light can escape. Either way, the original star is gone. What existed before, the structure, the identity, the particular configuration of matter that made that star, has been obliterated. The death is complete. The promise is kept. This is how the story was supposed to go. This is the model that astronomers built over decades of observation and calculation. Stars are born, stars burn, stars die, and the death, whether gentle or violent, whether a slow cooling or a catastrophic explosion, is final. The universe does not issue exceptions. It does not grant reprieves. A star that has reached the end of its fuel, a star that has undergone the collapse and explosion, is gone. There is a certain dark comfort in the completeness of that picture. The universe, for all its strangeness, at least seemed to follow its own rules. Death was death. Destruction was destruction. A supernova was an ending, not a transition. But then the observations began. And the observations told a different story. Because not every explosion follows the rules. Not every death is complete. And somewhere in the vast dark of the galaxy, there are things drifting through space that should not exist. Things that experienced what should have been total annihilation and survived. Charred and broken and wrong in ways that take time to fully comprehend, but undeniably, stubbornly, impossibly present. The universe had broken its own promise, and the door to something much stranger than a simple stellar death began to open. Let us return now to the white dwarf. Let us sit with it more carefully this time. Let us let the full strangeness of it settle into focus. Because the white dwarf is not simply a dead star. It is something more complex than that. It is something that occupies a position at the edge of what physics allows, a thing that exists right at the boundary of several fundamental laws. And it is this boundary existence that makes it the perfect starting point for a story about stars that refuse to die. Picture it. A sphere roughly the size of the Earth, perhaps somewhat larger, perhaps somewhat smaller, floating in space. From a distance, it glows. Not with the warm orange or yellow of a burning star. Not with the fierce blue-white of a young massive star. But with a pale, cool, blue-white or yellowish light that is the residual glow of a thing that is burned out. The surface temperature of a newly formed white dwarf can be over 100,000 degrees. Even after billions of years of cooling, it may still be thousands of degrees at the surface. Hot, yes, but not generating new heat. Simply radiating the heat it has stored. A white dwarf produces no new energy. There is no nuclear burning in its core. The fusion that sustained it for billions of years is finished. What keeps it from collapsing further under its own enormous gravity, what prevents it from simply imploding into something even denser, is not energy at all. It is a quantum mechanical effect called electron degeneracy pressure. This requires a moment of explanation because it is genuinely strange. In normal matter, the atoms and electrons that make up a substance can be compressed only so far before the electrons push back, simply because they need space to move. But in a white dwarf, the density is so extreme that the electrons have been pushed into the closest possible proximity. And at this point, a law of quantum mechanics called the Pauli exclusion principle comes into play. No two electrons can occupy the same quantum state at the same time. It is a fundamental rule of the universe. And this rule, this quantum restriction, produces a pressure that is unlike anything in ordinary physics. It is a pressure that does not depend on temperature. It does not depend on heat. It is simply a consequence of the density of electrons and the laws of quantum mechanics. A white dwarf is supported against gravitational collapse, not by the fire of nuclear fusion, but by the sheer quantum stubbornness of its electrons. It is held up by a law rather than by a force in the conventional sense. And this gives the white dwarf a quality of strange permanence. It will not collapse further. It cannot collapse further unless something adds mass to it. And it will not reignite on its own because there is no mechanism to restart the fusion. It will simply cool degree by degree for billions upon billions of years. Eventually, in a time frame so long it makes the current age of the universe look like an afternoon, a white dwarf will cool to the point where it no longer emits visible light. It will become what is sometimes called a black dwarf, a cold, dark, inert sphere drifting through space, a relic so ancient it has outlasted everything else around it. But here is the important thing. Here is the detail that opens the door to everything we are building toward tonight. A white dwarf is not isolated from the universe around it. It exists in space, and space is not empty. Space contains other stars, other bodies, other sources of mass and gravity. And sometimes, perhaps more often than was once appreciated, a white dwarf does not exist alone. Some stars are born in pairs. They form together from the same collapsing cloud of gas, two stars bound to each other by gravity, orbiting each other in a binary system. They spend their entire lives in each other's gravitational embrace. They burn together, evolve together, and die, not always at the same time. If one star in the pair is somewhat more massive than the other, it will burn faster and die first. And if it dies in the way of a smaller star, shedding its outer layers and leaving behind a white dwarf, then suddenly you have a very particular and very dangerous configuration. You have a white dwarf and a companion star orbiting each other. The companion is still alive, still burning, still expanding in the normal course of its own evolution. And the white dwarf is there, waiting, dense and patient, its gravity focused and precise. As the companion star evolves and expands, as it begins to swell outward in its own later stages of life, a moment eventually arrives. The outer layers of the companion begin to drift close enough to the white dwarf that the white dwarf's gravity can reach them. And the white dwarf begins to pull material from its companion. Hydrogen, the most abundant element in the companion star, begins to flow across the gravitational divide, spiraling down toward the white dwarf in a swirling stream, accumulating on its surface in a thin, growing layer. This process is called mass transfer, and it is, in the context of our story tonight, the beginning of the end, or perhaps more accurately, the beginning of what happens just before the end, and then, in certain strange and disturbing cases, just after the end as well. The hydrogen accumulates on the surface of the white dwarf. Day after day, year after year, century after century, the layer grows. The hydrogen is compressed by the white dwarf's enormous surface gravity, heated by the heat radiating from the dense core below. And eventually, something happens. The hydrogen layer reaches a critical temperature and pressure. The hydrogen ignites, not in the sustained, controlled fusion of a living stellar core, but in a sudden, violent flash, a thermonuclear detonation on the surface of the white dwarf. This surface explosion is called a nova, not a supernova, a nova. A flash of thermonuclear burning on the surface that blows the accumulated hydrogen layer outward into space in a brief, brilliant outburst of light. The white dwarf is not destroyed by this. It survives. The companion continues to transfer mass. And over time, the process repeats. The white dwarf is what astronomers call a recurrent nova, a star that periodically erupts as the hydrogen layer accumulates, ignites, and is blown away, again and again. But there is another possibility, a darker possibility, a possibility that, in the right circumstances, turns the nova into something far more destructive. If the mass transfer continues, and if the white dwarf accumulates more and more material without simply blowing it away in surface explosions, the mass of the white dwarf itself begins to grow. Not the layer on top, but the total mass of the white dwarf, deep inside its degenerate core. And as the mass grows, the electron degeneracy pressure that holds the white dwarf up against gravity is pushed closer and closer to its limit. There is a limit. It is called the Chandrasekhar limit, named for the physicist Subramanian Chandrasekhar, who calculated it in the 1930s. It is approximately 1.4 times the mass of the Sun. This is the maximum mass that a white dwarf can sustain while being supported by electron degeneracy pressure. Beyond this limit, the electrons cannot provide enough pressure to resist gravity. The white dwarf will collapse. But a white dwarf approaching the Chandrasekhar limit does not simply collapse quietly. Because as its mass increases and the pressure in its core rises, the temperature also rises. And carbon and oxygen, the primary constituents of a white dwarf's interior, can undergo thermonuclear fusion under the right conditions. As the white dwarf approaches its mass limit, the carbon in its core begins to ignite. Not gradually, not in a controlled way, but in a runaway thermonuclear reaction that propagates through the entire star in a fraction of a second. An explosion that makes a nova look like a match being lit in a hurricane. This is the Type Iax supernova. This is the death of a white dwarf that pushed its mass too far. And it is the version of stellar death that astronomers long believed was absolute. The white dwarf that undergoes a Type Iax supernova is completely and totally destroyed. Every bit of it is flung outward in the explosion. No remnant survives. The star simply ceases to exist. This was the model. This was the accepted picture. The white dwarf grows, reaches its limit, detonates, and is gone. Clean and complete and final. And then someone looked more carefully at the data. And the data showed something that did not fit. There are numbers in physics that feel abstract. Numbers that exist comfortably inside equations, that serve their function in the mathematics without ever acquiring any weight outside of it. Numbers you can write down, manipulate, substitute into other equations, and set aside without feeling that you have touched anything real. And then there are numbers that are different. Numbers that carry something more than their mathematical value. Numbers that mark a threshold, a boundary, a place in the space of physical possibility where one kind of thing ends and another kind begins. Numbers that, when you understand what they mean, stop being merely numbers and become something closer to a verdict. 1.4. 1.4 times the mass of the Sun. This is the Chandrasekhar limit. This is the number above which a white dwarf cannot survive. above which the electron degeneracy pressure that holds the white dwarf against gravitational collapse is no longer sufficient, above which the white dwarf must either detonate or collapse into something denser and more extreme. This is the number that means death for a white dwarf that has accumulated too much mass. The story of how this number came to be known is itself a remarkable one. Subramanian Chandrasekhar was a young Indian physicist, barely 20 years old, traveling by ship from India to England in 1930 to begin his graduate studies at Cambridge. During the voyage, sitting with the mathematics of stellar structure and quantum mechanics, he calculated the maximum mass that a white dwarf could sustain before electron degeneracy pressure would fail. He arrived at the number. He recognized what it meant. He was 20 years old, on a ship crossing the ocean, and he had just calculated the limit of a star's ability to resist its own death. The number he arrived at was not immediately accepted. The established astronomers of the time, including the formidable Arthur Eddington, found the implications of Chandrasekhar's result deeply uncomfortable, because what the result implied was that white dwarfs above this mass could not simply cool indefinitely. They had to do something else. They had to collapse further into something more compressed, something more extreme. And in 1930, the physics of what that something more extreme might be was not yet understood. Eddington preferred to believe that nature would find some way to avoid the conclusion that the universe would not permit stars to collapse into the kind of singularity that Chandrasekhar's mathematics implied. But the universe did not share Eddington's preferences. The mathematics was correct, the limit was real, and the objects that result from stellar collapse beyond the Chandrasekhar limit, neutron stars and black holes, were eventually discovered and confirmed, vindicating Chandrasekhar's calculation decades after he first made it. He was awarded the Nobel Prize in Physics in 1983, more than 50 years after the voyage during which he first worked out the number. 1.4 solar masses. But what does this number feel like when you try to hold it in the mind as something more than a quantity? A white dwarf at 1.3 solar masses is, by every measure, a stable and well-behaved object. Its electrons are under extraordinary pressure, compressed by the weight of more than a solar mass of material into a sphere roughly the size of the Earth. But they are managing. They are providing enough quantum mechanical resistance to hold the structure together. The white dwarf is cooling. It is dimming. It is proceeding, in its slow and patient way, through the billions of years of its cooling sequence. It is, for all its strangeness, doing what it is supposed to do. And then more mass arrives. More hydrogen flows across the gravitational bridge from the companion. More material accumulates on the surface. More of it is incorporated into the white dwarf's interior. The mass ticks upward. 1.31, 1.32, 1.35, 1.38. And with each increment, the pressure in the interior rises. The electrons are squeezed harder. The temperature at the center climbs. The carbon and oxygen nuclei that make up the white dwarf's interior begin to feel the conditions that will eventually allow them to fuse. They are not yet fusing. The temperature is not yet quite high enough, but the threshold is approaching. The margin between current conditions and the conditions needed for runaway thermonuclear burning is narrowing, degree by degree, as the mass climbs. 1.39. At this point, the white dwarf is a thing balanced on the edge of a knife. The electron degeneracy pressure is still holding. The nuclear burning has not yet ignited. The white dwarf still exists as a white dwarf, still radiates its quiet, cooling light, still occupies its orbit around the companion. But the internal conditions are approaching the point of no return. The carbon in the core is close to its ignition temperature. The density is at the level where the burning, once started, will propagate without the possibility of containment. 1.399. There is no drama visible from outside. The white dwarf does not tremble. It does not signal its distress. It does not change its outward appearance in any way that would tell an observer that the conditions inside it have reached the brink. It simply orbits, absorbs more mass, its interior creeping, degree by degree, toward the irreversible. And then the last few hundredths of a solar mass arrive. The temperature at the center reaches the ignition point for carbon fusion, and everything changes. Not gradually, not in the controlled and measured way that fusion proceeds in a living stellar core, but instantly, violently, in the way that a pressure vessel fails when the internal pressure finally exceeds the strength of the walls. The thermonuclear burning ignites. The runaway begins. The energy of the nuclear fire floods through the white dwarf's interior faster than any mechanism can contain it. 1.4 solar masses. The verdict, when it arrives in a fraction of a second. The Chandrasekhar limit is not a number you approach gradually and feel yourself approaching. It is a number you cross without knowing you have crossed it until the crossing is complete. It is a number you cross without knowing you have crossed it until the crossing is complete. There is no warning. There is no transition state. There is the white dwarf on one side of the limit, cooling and orbiting and accumulating mass in its slow and patient way. And there is the supernova on the other side, the violence that the limit unleashes when it is exceeded. Between them, there is essentially nothing. No intermediate state, no partial transition. The limit is a wall, and on one side of it stands a stable object, and on the other side stands an explosion so complete that it should, in the standard model, leave nothing behind. But as we have been exploring tonight, the standard model is not the whole story. Because the Chandrasekhar limit describes the threshold for detonation, it does not guarantee the completeness of the detonation that follows. There is room, in the physics, for an explosion that begins, propagates partway through the white dwarf, and then stalls. An explosion that exceeds the limit without fully honoring what the limit is supposed to mean. The Chandrasekhar limit is supposed to be a point of no return, a threshold beyond which the white dwarf is committed to total destruction. And in most cases, it is. In most cases, the detonation that follows the crossing of the limit is complete, and the white dwarf is obliterated, and the limit keeps its implicit promise. But in some cases, the detonation is not complete. In some cases, the fire catches but does not burn all the way through. In some cases, the white dwarf crosses the Chandrasekhar limit and finds itself committed to an explosion that is real but insufficient, violent but not quite violent enough, catastrophic but not quite catastrophic enough to finish the job. In those cases, the limit is crossed and the verdict is delivered, but the sentence is not carried out in full. In those cases, the limit is crossed and the verdict is delivered, but the sentence is not carried out in full. The white dwarf survives, altered beyond recognition, marked by the explosion that failed to complete it, drifting into the dark with the scars of the crossing written into every atom of its altered composition. 1.4 solar masses. A number that means death for a white dwarf. A number that is, in almost every case, the last number before the ending. And in the rare, disturbing, universe rule-breaking exceptions, the number before something else entirely. The number before the beginning of the zombie star, before the birth of the undead, before the emergence of a thing that crossed the threshold of destruction and came out the other side. Not whole, not unchanged, not anything like what it was, but there. Impossibly, stubbornly, gloriously, and horribly there. Before we arrive at the moment when the rules broke, before we step through the door into the truly strange territory of zombie stars and failed explosions, let us stay for a while with the binary dance. Let us feel the full weight of what is happening in these systems before we witness what happens when it goes wrong. Or perhaps, What happens when it goes wrong in a very particular way that is different from how it is supposed to go wrong. Because there is something deeply and almost unbearably intimate about a binary star system. Two stars, born from the same cloud of gas, spinning around each other across millions of kilometers of space, held in each other's gravitational embrace for billions of years. They are not touching. They are not even close, in the human sense of the word close. But they are locked together by the most fundamental force in the universe. They cannot leave each other. They orbit and orbit and orbit. The more massive one burns faster. It lives a shorter life, as things that burn too brightly often do. It exhausts its fuel first, swells into a red giant, sheds its outer layers, and becomes a white dwarf while its companion is still a healthy, middle-aged star going about the slow business of hydrogen fusion. And now the configuration changes. Now one of them is alive and one of them is something else. One of them is radiating warmth and light and conducting the normal business of stellar existence. And the other is dense and dark and cooling, circling its companion with a gravity that, because of the white dwarf's extreme compactness, is actually quite formidable at close range. The companion star does not notice at first. The white dwarf is small, and its gravitational influence is only significant when you get close enough. And for a long time, the two simply orbit each other. The companion burns. The white dwarf cools. The universe continues its indifferent business around them. But then the companion begins to age. Stars do not remain on what astronomers call the main sequence forever. After billions of years of hydrogen burning, the core hydrogen is depleted. The core contracts. The outer layers of the star expand. It begins to swell, slowly at first, then with increasing pace, puffing up toward the orbit of its white dwarf companion. And here is where the dance begins to change. Here is where the gravitational architecture of the binary system starts to matter in a very concrete way. In any binary system, there is a region of space around each star where that star's gravity dominates over the gravity of its companion. These regions are called the Roche lobes, and they have a very specific shape, like two teardrop-shaped bubbles pressed together at a single point. These regions are called the Roche lobes, and they have a very specific shape, like two teardrop-shaped bubbles pressed together at a single point. As long as both stars are smaller than their Roche lobes, they are essentially separate objects, each contained within its own gravitational bubble. But when the companion star swells to the point where it fills its Roche lobe, everything changes. The material at the outermost edge of the companion is no longer firmly within the companion's gravitational control. It sits at the exact balance point between the gravity of the companion and the gravity of the white dwarf. And the white dwarf, which has been waiting in the darkness, begins to pull. The transfer of mass begins. Not in a sudden rush, but in a thin stream, a river of hydrogen flowing from the bloated outer layers of the companion across the gravitational bridge between them, spiraling inward toward the white dwarf. This stream of material does not fall directly onto the white dwarf. It carries angular momentum, the rotational energy of its orbit around the system, and so it spirals into a disk around the white dwarf before eventually settling onto the surface. This disk is called an accretion disk. Accretion disks are among the most beautiful and violent structures in the universe. As the material spirals inward through the disk, it heats up due to friction, glowing with increasing intensity as it falls toward the white dwarf. The inner edge of the disk, closest to the white dwarf, can reach temperatures of tens of thousands of degrees, glowing blue-white with the heat of falling matter. From a great enough distance, the accretion disk might be the most visible part of the system, outshining the companion star with its frictional luminosity. And all the while, the white dwarf receives. And all the while, the white dwarf receives. Material accumulates on its surface. Hydrogen piles up, gram by gram, ton by ton, year by year. And as the mass on the surface builds, and as we established in the previous part of our story, the temperature and pressure of that layer increase. Eventually, the surface layer ignites. The nova flashes. The accumulated hydrogen is blown away. But the white dwarf is slightly more massive than it was before. Not all of the accreted material is expelled in the nova. Some of it remains, incorporated into the white dwarf's core. And so over many cycles of accretion and nova, the white dwarf grows. This growth is, in a very real sense, the binary dance. Two stars orbiting each other, one of them slowly feeding the other slowly growing more massive and more dangerous. It is a dance that can last for millions of years. A slow and silent choreography of gas and gravity, visible only to the instruments of astronomers and invisible to everything else in the universe. But every dance has a climax. Every sustained piece of music has a moment where the tension that has been building finally releases. And for a binary system with a growing white dwarf, that climactic moment is the moment when the mass approaches the Chandrasekhar limit. As the white dwarf's mass creeps upward, degree by degree, toward 1.4 solar masses, the pressure in its interior rises. The electrons that provide degeneracy pressure are squeezed harder and harder together. The temperature of the core rises, and the carbon and oxygen that make up the interior of the white dwarf begin to reach the conditions needed for thermonuclear ignition. The standard picture, the picture that held for decades, says that what happens next is unambiguous. Carbon fusion ignites in the core of the white dwarf. Carbon fusion ignites in the core of the white dwarf. This ignition is not controlled. There is no gradual ramp-up. It is an instantaneous, complete thermonuclear detonation that propagates through the entire white dwarf in a fraction of a second. The energy released by this detonation, approximately 1 to 2 times 10 to the 44th joules of energy, which is more energy than the sun will release over its entire 10 billion year lifespan, is enough to completely unbind the white dwarf, to fling every atom of it outward into space, to leave nothing behind. The Type Ia supernova is, in the standard model, an act of total self-annihilation. The white dwarf does not leave a neutron star. It does not leave a black hole. It does not leave a cooling core. It leaves nothing but an expanding cloud of debris, heavy elements synthesized in the explosion, iron and nickel and other products of the runaway fusion, spreading outward into space at tens of thousands of kilometers per second. And this is actually tremendously useful to astronomers, because Type Ia supernovae are remarkably consistent. They all detonate at approximately the same mass, near the Chandrasekhar limit, and so they all release approximately the same amount of energy. They all reach approximately the same peak brightness. This consistency makes them what cosmologists call standard candles, objects of known intrinsic brightness that can be used to measure distances. If you see a Type Ia supernova and measure its apparent brightness, you can calculate how far away it must be. It was this technique, using Type Ia supernovae as standard candles, that led to the discovery of dark energy and the accelerating expansion of the universe. Arguably the most important cosmological discovery of the 20th century. All of this rested on the assumption that Type Ia supernovae were clean and complete. All of this rested on the assumption that Type Ia supernovae were clean and complete. That every time a white dwarf reached the Chandrasekhar limit and detonated, the result was the same. Total destruction. No remnant. No survivor. And then astronomers began to find events that did not fit. Events that looked like Type Ia supernovae but were fainter, dimmer, less energetic. as though the explosion had been real but incomplete, as though the fire had caught but had not quite burned through. These events were labeled Type Iax supernovae, and what they implied, what the data slowly and uncomfortably forced astronomers to confront, was a possibility so strange, so contrary to the established order of stellar death, that it initially met with considerable resistance. The possibility that the explosion had not destroyed the white dwarf, that something had survived, that the white dwarf, having undergone what should have been its total annihilation, was still there. Broken, battered, barely recognizable, but there. A stellar corpse that was somehow not quite a corpse. A zombie star. And with that word, everything changes. Because now we are no longer talking about the orderly, rule-following physics of normal stellar death. We are talking about something that violates the very framework that makes Type I supernovae useful as cosmic measuring tools. We are talking about something that should not exist, being found not only in the data, but eventually in the sky itself. The dance is over. The climax has been reached, but the ending is not the one the music promised. And in the space between what was expected and what was found, something dark and strange and genuinely unsettling has taken up residence. Something with a light that should not still be shining. Something with a light that should not still be shining. Something that drifts through the galaxy bearing the marks of a catastrophe that should have ended it entirely. Something that survived its own death. Let the weight of that settle. Let the darkness around you be still. Because the story is about to go somewhere that even the universe was not supposed to allow. There are moments in the history of science when a single observation, a single measurement, a single data point collected by a patient and careful pair of eyes pressed against an eyepiece in the dark changes everything. Not gradually, not through the slow accumulation of evidence over decades, but suddenly, violently, the way a window shatters when something strikes it with enough force. One moment the glass is there, solid and transparent and reliable. The next moment it is gone, and the air that was on the other side comes rushing in. The discovery of supernovae was one of those moments. Not a single moment, actually, but a series of them, spread across centuries of observation, each one adding another crack to the glass of what was understood until finally the entire old picture gave way and something new and stranger took its place. Long before the word supernova existed, before the science of astrophysics had even been invented, people looked up at the sky and saw things that should not have been there. Stars that appeared suddenly where no star had been seen before. Stars that blazed with light for days or weeks or months, and then faded and were gone. The Chinese astronomers of the 11th century recorded one such event, a star that appeared in the sky in the year 1054 and was bright enough to be visible in daylight for 23 days. They called it a guest star, a visitor, something that came and stayed for a while and then left. They called it a guest star, a visitor, something that came and stayed for a while and then left. What they had witnessed was the death of a massive star. What they had seen blazing in the daytime sky was the light of a stellar explosion so violent that it had released, in the span of a few seconds, more energy than the sun would produce over 10 billion years. What remains of that event today, nearly 1,000 years later, is still visible through telescopes, an expanding cloud of glowing gas and filaments spanning roughly 11 light years, still spreading outward from the point of the explosion. At its center, spinning 30 times a second and emitting beams of radiation like a cosmic lighthouse, is the neutron star left behind by the collapse. We call this remnant the Crab Nebula, and it is, in a way, one of the universe's most eloquent monuments to the completeness of stellar death. The star is gone. What remains is not the star, but the aftermath of its destruction, a cloud of debris and a collapsed remnant that bears no resemblance whatsoever to the original object. The identity of the star has been erased. What existed before no longer exists in any meaningful sense. This is what supernovae do. This is their defining characteristic. They do not merely end a star's life in the way that the death of a sun-like star ends it, through a gradual fading into the quiet darkness of a white dwarf. They obliterate. They annihilate. They take the structure and identity of a star and reduce it to something so fundamentally different from what it was that the word transformation seems almost too gentle. Supernovae are among the most violent events in the observable universe. They release more energy in their first few seconds than the sun will release in its entire lifetime. They synthesize the heavy elements that make up everything around us, including the calcium in our bones and the iron in our blood. They are both destroyers and creators, endings that are also, in a cosmic sense, beginnings. The Type Iax supernova, the kind that involves a white dwarf in a binary system, is particularly interesting because of its mechanism. We discussed how the white dwarf accumulates mass from its companion, how that mass pushes the white dwarf toward the Chandrasekhar limit. But the exact process by which the explosion ignites and propagates through the white dwarf is something that took decades of careful theoretical work to understand, and even now, certain details remain the subject of active research. What seems to happen is this. As the white dwarf's mass approaches the critical limit, the pressure and temperature in its carbon-oxygen core rise to the point where carbon fusion can begin. But in a white dwarf, unlike in the core of a living star, the fusion does not proceed in a controlled and regulated way. There is no mechanism to adjust the rate of burning in response to changing conditions. The fusion simply begins and releases energy, and that energy heats the surrounding material, which then also fuses, which releases more energy, which heats more material. The fusion simply begins and releases energy, and that energy heats the surrounding material, which then also fuses, which releases more energy, which heats more material. A runaway process. A nuclear chain reaction that propagates outward from the ignition point at a significant fraction of the speed of sound within the star. The entire white dwarf, every bit of it, undergoes this runaway thermonuclear burning in roughly 1 second. 1 second. In the span of a single second, approximately 1.4 solar masses of carbon and oxygen are converted into heavier elements, primarily nickel-56, which subsequently decays into cobalt and then iron. The energy released by this burning is so enormous that it completely overwhelms the gravitational binding energy of the white dwarf. There is simply not enough gravity to hold the star together against the explosive force of the thermonuclear detonation. The white dwarf is unbound. Every atom of it is ejected into space at velocities ranging from 10,000 to 30,000 kilometers per second. In the span of a few hours, the white dwarf has expanded from an object the size of the Earth to an expanding shell of plasma thousands of kilometers across. In the span of a few days, it becomes the brightest thing in its galaxy. In the span of weeks, it begins to fade, the light from the radioactive decay of nickel and cobalt powering a gradual dimming that follows a characteristic curve. This characteristic light curve is one of the things that makes Type Iax supernovae so useful as standard candles. Because they all follow roughly the same pattern, they all reach roughly the same peak brightness, and that brightness can be measured and used to calculate distance. Because they all follow roughly the same pattern, they all reach roughly the same peak brightness, and that brightness can be measured and used to calculate distance. This is how, in the late 1990s, two independent teams of astronomers using Type Iax supernovae to measure the expansion of the universe discovered that the expansion was not slowing down, as expected, but accelerating. A discovery so unexpected, so contrary to what any existing model predicted, that it forced the introduction of a new component into the equations of cosmology, the component we now call dark energy. But notice what this entire framework of measurement rests on. It rests on the assumption that Type I supernovae are consistent, that they all detonate at the same mass, that they all release the same energy, and most importantly, that they are all complete. That every Type I supernova destroys its white dwarf entirely, leaving no remnant. Because if some of them are incomplete, if some of them fail to fully detonate and leave a surviving remnant behind, then the standard candle relationship is no longer as clean as assumed. And the cosmological conclusions drawn from it become less certain. This is part of why the discovery of Type Iax supernovae matters beyond its inherent strangeness. It is not merely an astronomical curiosity, a Gothic footnote in the catalog of stellar deaths. It has implications for our understanding of the universe's expansion, for the reliability of our distance measurements, for the very framework of modern cosmology. The zombie star is not just a haunting image. It is a wrench thrown into the machinery of some of our most carefully constructed scientific models. But let us not rush ahead. Let us stay for a moment more with the conventional supernova. Let us feel the full weight of what it is supposed to mean when a white dwarf explodes. Let us stay for a moment more with the conventional supernova. Let us feel the full weight of what it is supposed to mean when a white dwarf explodes. In the aftermath of a Type I supernova, there is nothing left of the white dwarf. The location where it once existed is marked only by an expanding cloud of ejected material, glowing with the radioactive decay of the elements synthesized in the explosion. The companion star, if it survives the blast, is left suddenly alone in space, stripped perhaps of some of its outer layers by the shockwave, set adrift at high velocity now that the gravitational anchor of its binary companion is gone. But there is no remnant of the white dwarf itself, no cooling core, no battered survivor, nothing. The completeness of this destruction was, for a long time, a point of pride in the theory. It fit so neatly. It made Type I supernovae so predictable, so measurable, so useful. The white dwarf grows to a specific mass, detonates completely, leaves nothing behind. Clean, elegant, final. Nature, however, does not always cooperate with elegance. Nature does not care about the convenience of our models or the neatness of our categories. Nature simply does what the laws of physics allow, and it turns out that the laws of physics allow things that nobody anticipated. There is a version of this story where the detonation is incomplete, where the thermonuclear flame that ignites in the white dwarf's core does not successfully propagate through the entire star, where the explosion is real but insufficient, where the energy released is enough to partially unbind the white dwarf, to strip away much of its outer layers and fling them into space, but not quite enough to completely destroy what remains at the center. A fizzle, a failed explosion, an attempt at total annihilation that falls short. A failed explosion, an attempt at total annihilation that falls short. And what is left behind when an explosion falls short is something that has no name in the conventional lexicon of stellar death. Something that is not a white dwarf, because it has been torn and scorched and altered beyond recognition. Something that is not a nova remnant, because the explosion was far too powerful. Something that is not a neutron star, because the core never collapsed far enough. Something new. Something that wears the marks of catastrophe on its entire surface. Something that drifts through space as evidence of a rule that was broken. A stellar ghost. A charred and mutilated survivor of an event that was supposed to be terminal. And the universe, indifferent as always, simply lets it drift. There is a particular horror in the thing that almost works. In the mechanism that engages but does not complete. In the process that begins with every indication of following its prescribed course and then, at the crucial moment, falls short. We recognize this quality in human experience. The plan that comes so close to succeeding before it fails. The escape that is almost complete before the door swings shut again. There is something about the almost, about the not quite, that carries a specific weight, a specific quality of wrongness that a clean failure somehow lacks. A clean failure is comprehensible. It failed. It did not work. We understand failure. We have categories for it. We have ways of processing it. We can look at a thing that has clearly and completely failed and make sense of it. But the thing that almost succeeded, the thing that got far enough that it should have worked, the thing that came within a breath of completion and then stopped, this thing lives in a different category entirely. It is the category of the uncanny, the category of the wrong. It is the category of the uncanny, the category of the wrong, the category of the thing that should not be. Type Iax supernovae are the universe's version of this. They are the almost, the not quite. The thermonuclear detonation that began, propagated partway through the white dwarf, and then ran out of energy before it could finish what it started. Let us be precise about what this means, because precision matters here. The difference between a Type Ia supernova and a Type Iax supernova is not simply a difference of degree, as though a Iax is merely a smaller, less energetic version of the same event. The difference is qualitative. It is a difference in kind. And that qualitative difference is what makes the Iax so strange and so significant. In a standard Type Ia supernova, the thermonuclear flame that ignites in the core of the white dwarf is a detonation. It propagates faster than the speed of sound in the stellar material. It moves so quickly through the star that the star has no time to respond, no time to expand and cool before the flame has already consumed it entirely. The entire white dwarf is burned in less than a second. The result is complete unbinding of the star. Nothing survives. In a Type Iax supernova, the picture is different. The current leading theoretical model suggests that in an Iax event, the thermonuclear flame ignites but propagates as a deflagration rather than a detonation. A deflagration is a slower process. It moves at less than the speed of sound in the stellar material. And this slower propagation has consequences. Because the flame is moving slowly enough, the white dwarf has time to respond. As the burning proceeds through the interior, the energy being deposited expands the star. The outer layers begin to move outward. As the burning proceeds through the interior, the energy being deposited expands the star. The outer layers begin to move outward. And as the star expands, the density in the remaining unburned material drops. And as the density drops, the conditions become less favorable for continued nuclear burning. The flame slows further. It becomes less efficient. And at some point, the remaining unburned material has expanded and cooled enough that the deflagration simply stops. It runs out of the conditions it needs to continue. The explosion has fizzled, but it has not done so without consequences. The energy that was released during the partial burning, while not enough to completely unbind the star, is still enormous by any human standard. It is more than enough to eject a significant fraction of the white dwarf's material. The outer layers, the regions that were consumed by the deflagration, the processed material of nickel and intermediate mass elements that resulted from the partial burning, these are flung outward into space. The white dwarf loses mass, perhaps the majority of its mass. It is stripped and scoured by the explosive process. But the inner core survives. Not the inner core as it was before. Not the calm, cool, degenerate interior of a white dwarf that has been quietly accumulating mass for millions of years. What survives is something beaten and scorched and fundamentally altered. Something that has been through the beginning of a nuclear detonation. Something whose composition and structure have been changed by the partial burning. Something that carries the physical marks of an event that should have been its total destruction. This surviving remnant is what we call the zombie star. And when you pause to think about what it actually is, what it represents, the image becomes genuinely disturbing in a way that goes beyond the gothic aesthetic of the name. This surviving remnant is what we call the zombie star. And when you pause to think about what it actually is, what it represents, the image becomes genuinely disturbing in a way that goes beyond the gothic aesthetic of the name. A zombie star is a stellar core that has experienced its own attempted annihilation and not been annihilated. It has felt the thermonuclear flame moving through its interior. It has absorbed the energy of its own partial explosion. It has been partly burned, partly ejected, partly consumed, and what remains is something that is, in a very literal physical sense, the survivor of an event whose purpose was its complete elimination. The question of what such a thing looks like, of what properties it has, of how it behaves in the aftermath of this catastrophe, is one that astronomers and theorists have been working to answer ever since the first Type Iax events were identified. And the answers, when they come, are strange. The surviving remnant is expected to be substantially less massive than the original white dwarf. Much of the material has been ejected in the explosion. The precise fraction depends on the details of how the deflagration proceeded, how much of the star it consumed before it stalled, but models suggest that the surviving remnant might retain anywhere from a small fraction to perhaps half the mass of the original white dwarf. It is expected to be highly inflated. The energy deposited by the partial burning expands the remnant, puffing it up far beyond the normal size of a white dwarf. Where a typical white dwarf is roughly the size of the Earth, a zombie star remnant might be many times larger in the immediate aftermath of the explosion, though it would gradually contract as it cools. It is expected to be hot. The explosion heats it thoroughly. It is expected to be hot. The explosion heats it thoroughly. The surface temperature of a freshly formed zombie star is expected to be extremely high, far hotter than a typical newly formed white dwarf. It radiates intensely in the ultraviolet and even in X-rays immediately after the event. And it is expected to be moving. This is one of the most remarkable predicted properties of zombie stars, and one of the key pieces of observational evidence that would allow them to be identified. When the white dwarf partially detonates, the material ejected in the explosion carries momentum. By Newton's third law, an equal and opposite momentum must be imparted to the surviving remnant. The explosion does not proceed symmetrically in all directions simultaneously. It begins at a particular point, proceeds in a particular pattern, and the asymmetry of the partial explosion gives the surviving remnant a kick, a sudden velocity imparted by the rocket-like effect of the ejected material. A zombie star should be moving fast, potentially moving fast enough that its velocity stands out dramatically from the normal background of stellar motion in its neighborhood. A stellar ghost on the run, a charred survivor fleeing the scene of its own attempted destruction. And this predicted high velocity would turn out to be one of the crucial pieces of evidence when astronomers finally found one. Because they did find one. Or rather, they found something that had been in the data all along. Something that had been cataloged and measured and filed away without anyone quite recognizing what they were looking at, until the theoretical predictions of zombie stars gave them a framework to see it. The universe had already placed the evidence in front of them. It had already provided the example. The universe had already placed the evidence in front of them. It had already provided the example. It had already created the thing that should not exist and sent it drifting through the galaxy, where it could eventually be discovered by the instruments and the patience and the theoretical framework of the people looking for it. And when they finally recognized it for what it was, when the pieces came together and the impossible object resolved into something with a name and a history and a set of measured properties, the feeling in the astronomical community was, by all accounts, something between exhilaration and unease. Because finding something that should not exist is a very different experience from predicting that it might. Prediction is a theoretical exercise. It is the manipulation of equations, the exploration of parameter space, the asking of what-if questions in a framework of controlled uncertainty. But finding it is different. Finding it means it is real. Finding it means the universe has done the thing the universe was not supposed to do. And the thing the universe had done was leave a survivor. It had started a supernova and failed to finish it. And in the space between the beginning of the explosion and its incomplete end, something had endured. Something charred and broken and wrong by the standards of every model of stellar death ever constructed. Something that was neither fully alive nor fully dead. Something that wandered the dark between the stars with the marks of its catastrophe written across every atom of its surface. Something that refused the grave. There is an ancient human intuition that the dead should stay dead. It appears in stories from every culture, in every age of recorded history, woven into folklore and mythology and religion and literature with such consistency that it begins to feel less like a cultural preference and more like a fundamental expectation, something close to a law that we believe the universe ought to follow. The dead do not return. The destroyed does not reassemble. The annihilated does not persist. And yet the universe, as we are learning tonight, does not share this intuition. The universe has no preference for clean endings. It has no investment in the narratives that make sense to the minds that have emerged within it. It simply follows the laws of physics wherever they lead, and sometimes, rarely but undeniably, the laws of physics lead to a place that feels, to our human sensibilities, like something between a miracle and a horror. The resurrection of a zombie star is not a miracle in any supernatural sense. It is physics. It is the consequence of a particular set of initial conditions, a particular configuration of mass and composition and temperature and pressure, interacting in a particular way to produce an outcome that was, for a long time, not predicted by the models. But just because it is physics does not mean it is not extraordinary. Just because it has a mechanism does not mean it is not disturbing. Let us walk through what actually happens. Let us follow the sequence of events from the moment the thermonuclear flame ignites in the white dwarf's core to the moment when the surviving remnant first finds itself alone in space, battered and glowing and profoundly altered. The ignition happens somewhere in the interior of the white dwarf. The ignition happens somewhere in the interior of the white dwarf. The exact location and the exact conditions that trigger the onset of the deflagration are still the subject of theoretical investigation. But for our purposes tonight, the important thing is simply that it begins. A nuclear flame springs into existence within the dense carbon-oxygen interior, and it begins to spread. The flame spreads outward. It consumes the material around it, converting carbon and oxygen into the products of nuclear burning, primarily nickel-56 and intermediate mass elements like silicon and sulfur and calcium. This burning releases energy. The energy heats the material around the flame front. The heated material begins to rise, buoyancy-driven convection pulling the hot, burnt material upward, while cooler, unburned material sinks inward. The geometry of the burning becomes complicated, turbulent, shaped by the internal dynamics of the star as it begins to respond to the energy being deposited. And as the star responds, as the outer layers begin to feel the pressure wave from the burning interior and start to expand outward, the conditions for continued burning begin to change. The density drops. The temperature in the unburned regions does not rise fast enough to ignite them before they have expanded out of the range where spontaneous nuclear burning is possible. The flame slows. The deflagration loses its coherence. It becomes patchy, uneven, energetically inconsistent. And then it stops. There is a moment, a physical moment, when the thermonuclear fire within the white dwarf simply ceases to propagate. The remaining unburned material has expanded and cooled to the point where it cannot sustain the burning. The flame dies, and what is left is a white dwarf that is partly burned, partly intact, violently disrupted, and in the process of flying apart, but not completely so. The outer layers, the material that was consumed by the deflagration and converted into the products of nuclear burning, are moving outward at high velocity. They are already committed to the expansion. They cannot return. They carry with them the energy of the partial explosion and the light curve signature that will eventually be detected by astronomers as a Type Iax supernova. They will expand and cool over the following days and weeks and months, producing the characteristic faint, blue, fast declining light curve that distinguishes an Iax event from its more energetic Type I cousins. But the inner core, the inner, unburned, or partially burned central regions of the white dwarf, these do not have the velocity to escape. The energy deposited by the deflagration has puffed them up, has inflated them, has deposited heat throughout their bulk. But they do not have enough kinetic energy to unbind themselves from their own gravity. They fall back. They reassemble. They coalesce into a single, hot, bloated, chaotic object. This is the birth of the zombie star. Not a gentle birth, not an orderly one, but a traumatic, violent, physically catastrophic emergence into a new state of being. The zombie star comes into existence not as a creation, but as a survivor, something defined not by what it is becoming, but by what it has endured. In the immediate aftermath, the zombie star is enormous and bright. It is inflated far beyond the normal dimensions of a white dwarf, expanded by the heat deposited throughout its bulk. Its surface glows intensely, radiating the thermal energy of the explosion that created it and failed to destroy it. It is, in the initial period following the event, one of the brighter objects in its local neighborhood, though it is fading, gradually contracting, slowly cooling. But there is something profoundly different about the way a zombie star cools compared to the way a normal white dwarf cools. A normal white dwarf, settling into its long cooling sequence after the death of its progenitor star, is a remarkably stable and well-understood object. Its cooling follows predictable curves. Its composition is relatively uniform. Its structure, while exotic by terrestrial standards, is well characterized and well modeled. A zombie star has none of this stability. Its interior is a jumble, a chaotic mixture of unburned carbon and oxygen from the original white dwarf, partially burned material from the regions where the deflagration did its work, and the products of complete nuclear burning from the core, where conditions were most extreme. It is compositionally inhomogeneous in ways that are difficult to model precisely. It is thermally disequilibrated, meaning that the temperature distribution within it is uneven and complex. It is structurally disrupted, its internal layers scrambled by the turbulent convection of the burning and the violence of the explosion that failed. It is not a clean object. It is a messy one, a complicated one that bears the fingerprints of a catastrophic event in every layer of its interior. And it is moving. As predicted by the theoretical models, the asymmetry of the partial explosion has given the zombie star a kick, a velocity imparted by the uneven distribution of the explosive ejecta. The zombie star is not simply floating in the space where its progenitor white dwarf once orbited. It has been set in motion. It is traveling, perhaps slowly by cosmic standards, but measurably, detectably, in a direction determined by the geometry of its incomplete destruction. This motion is important, not only as a piece of physical evidence that confirms the zombie star's identity, but as a deeply evocative detail. Not only as a piece of physical evidence that confirms the zombie star's identity, but as a deeply evocative detail. A zombie star is a wanderer. It is not anchored. It is not contained. It has been cut loose from its binary companion by the violence of the explosion that killed the system they shared, and it drifts now through the galaxy without a fixed address, without a gravitational home, carrying its history in its altered composition and its inflated structure and its unearned velocity. A stellar ghost, a drifting remnant of something that was supposed to have been completely erased, and it will drift for a very long time. White dwarfs, even disturbed and altered ones, even zombie stars, have lifetimes measured in billions of years. The cooling sequence is long. The thermal energy stored in the bulk of the object is enormous, and it radiates away slowly. The zombie star will drift through the galaxy for billions of years, gradually cooling, gradually contracting, gradually fading from the intense glow of its post-explosive state towards something dimmer and darker. But it will not disappear. It will not fade to nothing on any timescale that feels relevant to the stars around it. It will drift and cool and dim and drift and cool and dim. A charred remnant of something that tried to die and failed. A permanent reminder that the universe does not always keep its promise of annihilation. And the most disturbing thing about the zombie star, in some ways, is precisely this permanence. Not the violence of its creation, not the chaos of its interior, not the unnatural velocity of its motion, but the fact that it continues, the fact that it persists, the fact that, according to every model we had before the discovery of Type Iax supernovae, it should not be there, and yet, there it is. There it has been, all along. There it has been, all along, drifting through the galaxy, cooling and glowing with its undead light, waiting to be found. And found it was. We have been following the white dwarf. We have watched it accumulate mass, approach the limit, experience the ignition, survive the incomplete explosion. We have traced the birth of the zombie star from the perspective of the thing that survived. But there is another perspective. There is another presence in this story that we have not yet fully inhabited. Another object that was there, that participated in the events leading up to the explosion, that was present when the detonation occurred, and that survived the experience in a very different way. The companion star. Let us turn toward the companion now. Let us sit with its experience, insofar as a star can be said to experience anything. Let us follow what happens to it when the white dwarf it has been orbiting for millions of years suddenly detonates in a failed thermonuclear explosion that produces a zombie star and flings the outer layers of the white dwarf outward into space at tens of thousands of kilometers per second. The companion star, when the explosion occurs, is close. It has been close for the entire duration of the mass transfer process, orbiting the white dwarf at a distance small enough that its outer layers overflowed its Roche lobe and fed the white dwarf the mass it needed to approach the Chandrasekhar limit. The two objects have been in an intimate gravitational relationship for millions of years. They have circled each other, shaped each other's evolution, participated together in the long, slow build-up to the event that is about to occur. And then the event occurs. The outer layers of the white dwarf are flung outward at extraordinary velocity. The outer layers of the white dwarf are flung outward at extraordinary velocity. A shell of ejected material, the products of the partial nuclear burning, the unburned remnants of the outer regions, all of it moving outward in an expanding sphere that encompasses the orbit of the companion and passes over it in a matter of hours. The companion is struck, not with the full force of a complete Type Ia supernova, which would be even more energetic, but with the force of a Type Iax, a partial explosion that is nevertheless enormously powerful. The shockwave from the ejecta hits the companion's outer atmosphere. It strips material from the surface. It heats the facing side of the companion to extreme temperatures. It deposits energy throughout the companion's outer layers, energy that the companion will radiate away over the following months and years as a kind of afterglow, a secondary brightening that follows the main light curve of the supernova. And then, more fundamentally, something else happens. The gravitational anchor is gone. The white dwarf that the companion has been orbiting is no longer the white dwarf it was. It has been transformed. The zombie star that emerged from the explosion has a different mass, a different structure, a different velocity. And the zombie star has been kicked by the asymmetric ejecta in a particular direction. It is no longer in the same place. It is moving away. The gravitational relationship that held the binary system together, that determined the orbital dynamics of two objects circling each other for millions of years, has been abruptly and irreversibly disrupted. The companion is released. It is no longer in a binary orbit. It is no longer circling another object. The gravitational relationship that structured its existence for the last several million years has ended, not gradually, not through any process of natural dissolution, but in an instant, in the explosion that produced the zombie star and flung the remnant away. The companion is released. It is no longer in a binary orbit. It is no longer circling another object. The gravitational relationship that structured its existence for the last several million years has ended, not gradually, not through any process of natural dissolution, but in an instant, in the explosion that produced the zombie star and flung the remnant away. And the companion, which has been moving with the orbital velocity of the binary system, finds itself moving in a straight line, no longer constrained by the circular or elliptical path of the orbit, no longer pulled inward by the gravity of the white dwarf companion, simply moving in the direction it was moving at the moment the binary ended, at the velocity it had at that moment. This velocity can be significant. Depending on the orbital parameters of the binary system, the companion may be moving at hundreds of kilometers per second relative to the local galactic environment. It is now, from the moment of the explosion, a runaway star, a star that has been set free by the destruction of its binary companion and is moving through the galaxy at a speed that flags it as something unusual, something that requires an explanation, something with a history that is written in its velocity and in the marks the explosion left on its surface. The companion is a survivor too, but a different kind of survivor from the zombie star. The zombie star survived the explosion by being the direct target of it, by being the object at the center of the event, by enduring the thermonuclear fire in its own interior and emerging on the other side of it. The companion survived the explosion by being close to it, but not at the center of it, by being struck by the ejecta rather than consumed by the detonation, by being a bystander rather than the principal actor. The zombie star carries its survival in its altered composition, in the nucleosynthesis products mixed into its atmosphere, in the physical marks of the partial burning. The zombie star carries its survival in its altered composition, in the nucleosynthesis products mixed into its atmosphere, in the physical marks of the partial burning. The companion carries its survival in its velocity, in the surface heating from the ejecta impact, in the stripped outer layers and the elevated temperature of its facing hemisphere. Two survivors of the same event, marked in different ways, moving in different directions, separated now by the explosion that created the zombie star and released the companion. And the silence between them, after the explosion, is profound. For millions of years, these two objects had a relationship. Not a conscious relationship, not a felt one, but a physical one, as real and as structured as any relationship in the universe. They moved in response to each other's gravity. They exchanged mass across the bridge between their Roche lobes. They shaped each other's evolution. The white dwarf became what it became because of the companion's contribution. The companion evolved as it did because of the gravitational influence of the white dwarf. They were, in the most literal physical sense, connected. And then the explosion severed that connection. The zombie star moves in one direction. The companion moves in another. The distance between them grows. The gravitational force that once linked them fades with the inverse square of the increasing separation. In a few thousand years, they are so far apart that neither exerts any significant gravitational influence on the other. They have become, functionally, independent objects. Two strangers in the galaxy, moving on unrelated trajectories, bound together only by the shared event in their histories that set them both in motion. The companion does not know this. It has no awareness of the zombie star. It does not register the absence of its former companion any more than it registered the presence. It simply burns, fusing hydrogen in its core, evolving along the normal path of its stellar evolution, carrying in its elevated surface temperature and its unusual velocity the evidence of an event that is now receding into its past. And yet the marks are there. The companion star, if examined with sufficient precision, reveals its history. Its velocity is anomalous. Its surface composition shows evidence of the material that was deposited by the ejecta impact. Its luminosity and temperature profile may carry the lingering signature of the heating it received from the explosion. And if you know what you are looking for, if you have the theoretical framework to interpret these signatures, the companion star tells you its story as clearly as the zombie star tells its own. Different stories, told in different languages, by two objects that were once bound together and are now drifting apart into separate regions of the galaxy, each carrying the evidence of a shared catastrophe in its own body, in its own way. The zombie star is the horror story. The mutilated survivor, marked by the fire that tried to consume it, drifting with its undead light and its impossible composition. The companion is the other kind of story. The witness, the bystander who was close enough to be affected, who bears the marks of proximity to the catastrophe, but who was not the target, who did not feel the fire from the inside, who survived not by enduring the unsurvivable, but simply by being far enough from the center when the center failed to completely annihilate itself. Both kinds of stories are written in the sky. Both kinds of survivors are drifting through the galaxy right now, moving away from the locations of the events that created them, carrying their histories in the languages of velocity and composition and surface temperature. And the silence between them, the expanding space that separates the zombie star from the companion it once orbited, grows larger with every passing year. They will never meet again. The physics of their post-explosion trajectories makes this essentially certain. They are moving in different directions at high speeds. The space between them increases monotonically. The galaxy is large and they are small, and the probability of a chance re-encounter is vanishingly small. The binary system that produced them is gone. The relationship that lasted millions of years ended in a fraction of a second. And each of its two survivors drifts on alone, in the silence that followed the explosion, into the vast and indifferent dark. And each of its two survivors drifts on alone, in the silence that followed the explosion, into the vast and indifferent dark. Science does not always proceed through dramatic moments of revelation. It is rarely the case that a single observation, a single measurement, a single number appearing on a computer screen in a dim and quiet laboratory changes everything in an instant. More often, the path to discovery is slow and winding, made of years of data collection, failed hypotheses, revised models, patient disagreements between careful people. The truth emerges not like a light being switched on, but like a dawn, gradual, accumulated. The darkness receding degree by degree until suddenly, without any single moment of transition, it is day. But sometimes there is a moment that is close enough to the dramatic version that the distinction does not matter much. A moment when the data resolves into something so unexpected, so contrary to established understanding, so clearly extraordinary, that the people looking at it stop and look again and look a third time because they do not quite trust what they are seeing. The discovery of LP 40365 was something like that moment. LP 40365. The name is not evocative. It is not the kind of name that sounds like it belongs to the protagonist of a cosmic horror story. It is a catalog designation, a string of letters and numbers assigned to an object that had been cataloged long before anyone understood what it was. LP stands for Lutyens Palomar Survey, a photographic survey of the sky conducted in the mid-20th century. The number simply identifies this particular object within that catalog. It had been known to astronomers for decades as an unremarkable star. A faint object, visible only through telescopes, sitting at a distance of roughly 1,000 light-years from Earth in the direction of the constellation Lupus. Nothing about its initial cataloging suggested that it was anything other than what it appeared to be at first glance, a dim, somewhat unusual stellar object in an unremarkable patch of sky. But when astronomers began looking more carefully, when they began measuring its properties with the precision that modern instruments allow, the details that emerged did not fit any ordinary category. The first strange thing was its composition. When astronomers analyzed the light from LP 40365 spectroscopically, spreading its light into its component wavelengths to read the chemical fingerprints of the elements in its atmosphere, they found something deeply unusual. The spectrum showed strong signatures of oxygen and neon and magnesium, not hydrogen, which dominates the spectra of most stars, not helium, which appears in the spectra of hot compact objects. Oxygen and neon and magnesium, in proportions that did not correspond to any normal stellar atmosphere. These elements, particularly the specific mixture of them found in LP 40365, are not what you would expect to find in an ordinary star at any stage of its normal evolution. They are, however, precisely what you would expect to find in the surviving remnant of a partially burned white dwarf. They are the products and remnants of nuclear burning that was initiated but not completed. They are the fingerprints of a thermonuclear detonation that happened but did not finish. The composition of LP 40365 was, in other words, the compositional signature of a zombie star. But the composition alone, strange as it was not enough to be certain. There are other ways to produce unusual elemental mixtures in stellar atmospheres. Other explanations, some more contrived than others, that might account for what was observed. Before the full picture could be assembled, more data was needed. And the next piece of data was, if anything, more dramatic than the composition. LP 40365 is moving. Not with the gentle, unhurried velocity of an ordinary star going about its business of orbiting the center of the galaxy, but at a speed that immediately flags it as something extraordinary. Its velocity relative to the local standard of rest, the average motion of the stars in its neighborhood, is enormous. LP 40365 is moving at roughly 850 kilometers per second. To put that in some context, the orbital velocity of the Earth around the Sun is about 30 kilometers per second. Our sun's velocity around the center of the galaxy is about 220 kilometers per second. The typical random velocities of stars in the solar neighborhood are a few tens of kilometers per second above or below this galactic orbital motion. Even the hypervelocity stars, the unusual objects that have been accelerated by gravitational interactions with a massive black hole at the center of the galaxy, typically move at velocities of around 500 to 700 kilometers per second. Even the hypervelocity stars, the unusual objects that have been accelerated by gravitational interactions with a massive black hole at the center of the galaxy, typically move at velocities of around 500 to 700 kilometers per second. LP40365 is moving at roughly 850 kilometers per second. This means it is moving fast enough to escape the gravitational pull of the Milky Way entirely. It is not simply an unusual star in the neighborhood. It is an object that is, in the long run, leaving the galaxy. It was thrown out with enough velocity that even the gravity of 100 billion stars combined cannot bring it back. This extraordinary velocity is precisely what the zombie star models predicted. The kick imparted to a surviving remnant by the asymmetric partial explosion of its white dwarf progenitor. The rocket effect of the ejecta departing in one direction and pushing the remnant in the opposite direction. A velocity so high that it stands out immediately in any survey of stellar motion as something that requires a special explanation. And the combination of the unusual composition and the extraordinary velocity, taken together with the object's other measured properties, including its temperature and luminosity and size, which are consistent with a highly inflated, partially burned stellar remnant in a late stage of cooling, was enough. The pieces fit together. The picture resolved. LP40365 was, and is, a zombie star. A surviving remnant of a Type Iax supernova, a white dwarf that was partially exploded and partially survived. The first object of its kind to be conclusively identified and studied. A surviving remnant of a Type Iax supernova, a white dwarf that was partially exploded and partially survived. The first object of its kind to be conclusively identified and studied. The paper announcing this identification was published in 2017 by a team of astronomers led by Stefan Venus and colleagues, working with data from multiple telescopes and survey programs. The title of the paper was blunt and direct in the manner of scientific literature, but the content was anything but ordinary. It described, in the careful and measured language of professional astronomy, an object that should not exist according to any prior model. An object whose existence demanded a revision of the understanding of stellar death. An object that had survived its own supernova. The broader astronomical community's reaction was one of genuine surprise combined with, for those who worked on the theoretical models of Type Iax supernovae, a kind of vindication. The theorists had predicted that these survivors should exist. They had calculated their expected properties. And now here was one, right there in the data, matching the predictions with a fidelity that was, under the circumstances, both satisfying and deeply unsettling. Satisfying because the science worked. Because the predictions had been confirmed. Because the physical models had successfully anticipated the properties of an object that no one had previously observed. Because the physical models had successfully anticipated the properties of an object that no one had previously observed. Unsettling because what the science was confirming was the existence of something genuinely monstrous by the standards of stellar physics. Something that had no right to be there. A corpse that had gotten up and walked. A star that had died and refused the permanence of its own death. LP40365 is out there right now. As you read these words, as the night settles around you and the stars wheel overhead, somewhere roughly 1,000 light years away, in the direction of a constellation most people in the northern hemisphere have never seen. A zombie star is drifting through space at nearly 1,000 kilometers per second. It is smaller now than it was in the immediate aftermath of the event that created it. It has cooled and contracted over the thousands of years since the explosion, but it still glows. It still shines with a surface temperature high enough to emit strongly in the ultraviolet. It still carries in its peculiar atmospheric composition the unmistakable chemical signature of a thermonuclear catastrophe. It is, by every measure, what it appears to be. A thing that survived its own death. A stellar ghost that is, unlike most ghosts, entirely real, measurable, observable, undeniably present. And LP40365 is almost certainly not alone. If one zombie star has been found, others must exist. If one zombie star has been found, others must exist. The galaxy is large, and the survey programs that have examined it are incomplete. How many other objects like LP40365 are drifting through the Milky Way right now? Unrecognized, unidentified, listed in catalogs under uninformative designations. Waiting for someone to look closely enough to see what they really are is a question that researchers are actively working to answer. The zombie stars are out there, drifting in the dark, cooling slowly, carrying their histories in every atom of their peculiar compositions. And the night sky, which seems so orderly and so familiar, turns out to be haunted by them. There is a particular quality to the light of dying things. Perhaps you have noticed it. The way a fire looks different when it is burning down compared to when it is burning up. The way the last light of the sun, just as it sinks below the horizon, has a quality that afternoon light lacks. A warmth that is deeper somehow, a color that is richer, as though the diminishing is making the light more itself rather than less. This is partly physics and partly perception. But the perception is real even if the physics can explain it. We respond to the light of endings differently than we respond to the light of middles. The light of a zombie star has this quality, multiplied to an almost unbearable degree. Consider what you are seeing when you observe LP40365 or any other zombie star remnant. Consider what you are seeing when you observe LP40365 or any other zombie star remnant. You are not seeing the light of a living star, a star in the full vigor of nuclear burning, converting fuel into energy through the clean and ongoing process of stellar fusion. You are not seeing the light of a recently dead star, the bright flash of a fresh supernova, or the hot glare of a newly formed white dwarf. You are seeing something else entirely. You are seeing the residual glow of a catastrophe that was supposed to be terminal. You are seeing the light of something that endured what should have been its complete destruction, and is still here, still glowing, not because it is generating new energy, but because it has not yet finished radiating away the heat deposited by its own failed explosion. This is undead light. Light that has no right to exist by the rules of the universe as we understood them before the discovery of Type Iax supernovae. Light produced not by the orderly processes of stellar evolution, but by the chaotic aftermath of a broken rule, a violated expectation, an exception to the principle of stellar mortality that the universe has been quietly maintaining without anyone noticing. The spectrum of this light is strange. Not merely unusual in the way that many astronomical objects are unusual, sitting at the edge of the familiar distribution but still recognizably related to it, but genuinely, deeply strange. But genuinely, deeply strange. The prominent absorption features of oxygen and neon and magnesium that mark LP 40,365 spectrum do not match the spectrum of any normal class of star. They do not fit into the standard classification schemes that astronomers use to organize the stellar population. They are the spectrum of something new, something that requires its own category, something for which the existing vocabulary is inadequate. Astronomers are in the process of building that vocabulary. They are studying LP40365 and the handful of other candidate zombie stars that have been tentatively identified in recent years, trying to understand the full picture of what these objects are and how they evolve and what they can tell us about the physics of the events that created them. But the vocabulary is incomplete. The category is newly defined, and the light of these objects continues to carry its undead quality. Its fingerprint of catastrophe survived, its evidence of a rule that did not hold. There is something specifically Gothic about the spectrum of a zombie star. In Gothic literature and Gothic aesthetics, there is a recurring motif of the thing that looks alive but is not, the animation that persists after the appropriate moment of cessation, the warmth that has not yet faded from the corpse. The zombie star is this motif rendered in astrophysics. The zombie star is this motif rendered in astrophysics. It is still warm, still glowing, still radiating energy, but the process that should produce this warmth and glow and radiation has ended. It is warm with borrowed time. It is glowing with the heat of a violence that tried to consume it completely. And the color of that glow, the specific wavelengths that dominate its emission, tell a story about where the heat came from. A zombie star is hot. Its surface temperature, even thousands of years after the event that created it, is still high enough to produce significant ultraviolet radiation. In visible light, it would appear blue-white, the color of a hot compact object. But the most intense part of its emission is in the ultraviolet, invisible to the naked eye, accessible only to space-based telescopes that can see above the absorbing layer of Earth's atmosphere. This means that zombie stars are, in a sense, hidden. Not completely, not from every instrument, but from the casual observer, from the person standing in a dark field looking up at the sky with their own eyes. Zombie stars are invisible. LP40365 is a faint object, detectable only with telescopes, and even its intense ultraviolet emission is completely blocked from ground-based observers. They drift through the galaxy in a kind of enforced invisibility. Their most characteristic emission hidden by the atmosphere that shelters life on the only planet we know of that harbors it. Their visible light too faint to be seen without instruments. Their extraordinary velocities detectable only through the careful measurement of spectral shifts, the Doppler stretching of their light as they move away from or toward us at hundreds of kilometers per second. They are there, but they do not announce themselves. They do not blaze across the sky demanding attention. They drift quietly and relentlessly, carrying their history of survived catastrophe in wavelengths we cannot see and velocities we can only measure rather than feel. There is a silence to them that is almost the deepest thing about them. Not the silence of a thing that has never spoken, but the silence of a thing that has been through something so extreme that it has no way to communicate the experience in any language that another object can hear. The zombie star drifts alone, its peculiar light pouring outward in all directions, reaching the mirrors of telescopes on distant planets, entering the detectors of instruments built by minds that took billions of years to evolve, being processed into numbers that eventually resolve into a picture of something that should not be. And the something that should not be does not care whether it is found or not. It does not know it is extraordinary. It does not know it has broken a rule. It simply continues to exist, to cool, to drift, to shine with its undead light. The indifference of it is perhaps the most disturbing thing of all. In human stories of the undead, the monster is at least conscious of its monstrousness. It knows what it is. It responds to its condition with something, whether that something is horror or defiance or hunger or grief. It participates in the story of its own wrongness. The zombie star does not. It has no awareness of the theoretical frameworks that say it should not exist. It has no response to the astronomical papers written about it. It does not know that it is a violation of the models. It simply burns with the heat it was given. It drifts in the direction it was kicked. It carries its peculiar composition without any awareness that the composition is telling a story. And the story it tells, to those equipped to read it, is the story of a death that did not quite take. A destruction that was real but incomplete. A violence that scoured the surface and scorched the interior and flung the outer layers into space, but left something behind that is still, in some fundamental physical sense, there. The undead light of a zombie star is not metaphor. It is photons. It is real electromagnetic radiation, produced by real thermal processes, traveling through real space at the real speed of light to arrive at real detectors and be recorded in real data. But the meaning of it, the story that the light tells when you know how to read it, is something that the human mind reaches for in the vocabulary of the gothic, the uncanny, the existentially disturbing. Because the universe has done something that the universe was not supposed to do. Because the universe has done something that the universe was not supposed to do. It has allowed a death to be incomplete. It has permitted a survivor where no survivor should be. And it has sent that survivor drifting through the dark, glowing with a light that is, by the most literal physical definition, the light of a thing that refused to die. The galaxy is haunted, not by spirits or by metaphors, but by actual physical objects whose existence challenges the rules. By drifting, cooling, glowing remnants of catastrophes survived. And somewhere in the dark, right now, one of them passes through a region of space that no telescope is currently pointed at and emits its strange blue-white ultraviolet light into the void, and no one sees it. It does not mind. It has no mind to mind with. It simply drifts, and glows, and drifts. The undead light falling silently on nothing. There is a philosophy buried inside astrophysics. Not placed there intentionally, not written in as a footnote by the scientists who built the equations and ran the simulations and collected the data, but present nonetheless, the way a shadow is present wherever there is light. The physics of stellar death is, at its deepest level, a physics of endings. It is a set of rules about what happens when the processes that sustain a thing finally cease, about what is left behind, about whether anything is left behind at all. And for most of the history of this field, the philosophy was clean. The philosophy was one of finality. Stars are born, stars burn, stars die. And what death means, in this context, is the cessation of the processes that define the object as what it was. A star is defined by its fusion. When the fusion stops, the star is gone. What remains afterward, whether a white dwarf or a neutron star or a black hole, is not the star. It is a remnant. What remains afterward, whether a white dwarf or a neutron star or a black hole, is not the star. It is a remnant, a relic, something that occupies the space where the star was, but does not carry the star's identity forward in any meaningful sense. Death, in the conventional framework of stellar astrophysics, meant transformation so complete that it constituted erasure. This is a surprisingly coherent philosophical position when you sit with it. It says that identity is process, that a thing is what it does rather than what it is made of, that when the process ceases, the thing ceases, even if some of the material components of the thing persist in altered form. A star that has become a white dwarf is not a star that has died. It is a different kind of object that has come into existence in the place where the star used to be, made partly of the same material, but not continuous with the star's identity. This view of stellar death has a certain clarity to it, a certain philosophical rigor that makes it satisfying in a way that goes beyond its purely scientific content. It resolves the question of what death is for stars, with a definiteness that the corresponding question in biology and philosophy has never quite managed to achieve. For stars, at least, we knew. We had the physics. We had the equations. We knew what death meant. And then the zombie stars complicated everything. Because the zombie star is not simply a remnant. It is not a white dwarf that has come into existence in the place where a white dwarf used to be, made of different material, definable as a new and separate object. A zombie star is the white dwarf itself, physically continuous with what it was before, materially identical though structurally altered, bearing in its own body the evidence of a catastrophic event that should have ended it but did not. A zombie star is the white dwarf itself, physically continuous with what it was before, materially identical though structurally altered, bearing in its own body the evidence of a catastrophic event that should have ended it but did not. The zombie star challenges the philosophical position that death means transformation so complete that it constitutes erasure. Because the zombie star was transformed but not erased. It was altered beyond any easy recognition. Its surface composition was changed by the partial burning. Its internal structure was disrupted by the violence of the deflagration. Its position and velocity were altered by the asymmetric ejecta. It is not what it was, but it is still something. And that something is, in a physical sense, materially continuous with what it was before the explosion. If we say that the white dwarf died in the Type Iax supernova, what does that mean for the object that is clearly still there, still glowing, still drifting through the galaxy with the chemical fingerprints of the event written into its atmosphere? Was it the white dwarf that survived? Or is it a new object that happens to be made of most of the same material? These questions might sound like philosophical games, like the kind of abstraction that physicists tend to dismiss as outside their domain. But they are not. They are directly relevant to how we understand and classify and model these objects. The question of whether a zombie star is a surviving white dwarf or a new category of object entirely determines how we should model its cooling evolution, how we should interpret its spectrum, how we should calculate its expected future trajectory and fate. And there is a broader implication that extends beyond the immediate technical questions. The discovery of zombie stars forces a revision of the picture of what stellar death is. The discovery of zombie stars forces a revision of the picture of what stellar death is. Not a wholesale abandonment of the framework, not a revolution that discards everything that came before, but a complication, a nuancing, a recognition that the clean philosophical picture of death as complete transformation was a simplification that the universe does not fully honor. Stars can, it turns out, partially die. This phrase sounds almost nonsensical. Partial death. What does partial death mean? Either something is dead or it is not. Either the process that defines the object has ceased or it has not. There is no halfway. Or so the old framework implied. But the zombie star is a halfway. It is an object that has undergone what should have been a lethal event, that has been physically and chemically and dynamically transformed by that event, that has lost a significant fraction of its original mass to the explosion, that has been heated and disrupted and set drifting through space with an unusual velocity. And yet the core of it persists. The center of it survived. The physical continuity that would allow us to say this is still the same object was maintained through the catastrophe. The white dwarf did not fully die, and in not fully dying, it became something that the old framework of stellar death could not accommodate. Something that required not just a new entry in the catalog of stellar objects, but a new concept of what it means for a star to die. This has implications for the way we think about endings more generally. The universe, it turns out, does not deal exclusively in complete endings. It deals also in incomplete ones, in partial destructions, in catastrophes that stop just short of total annihilation. And these incomplete endings create objects, states of being, that the theory of complete endings never predicted and cannot fully account for. And these incomplete endings create objects, states of being, that the theory of complete endings never predicted and cannot fully account for. There is a quality to this realization that goes beyond astrophysics. It touches something in the human experience of endings, in the way we think about destruction and survival, and the things that persist in the aftermath of catastrophe. We tend to think of major disruptions in terms of complete before and after states. The thing existed. The catastrophe happened. Now the thing is gone and something else is in its place. But sometimes the catastrophe is real and the damage is genuine and the change is profound, and yet the thing is still there. Altered, scarred, structurally disrupted, compositionally changed, but there, present, continuing, refusing the complete transformation that the violence of the event seemed to demand. The zombie star is the universe's enactment of this experience. The universe demonstrating, in the language of plasma physics and nuclear astrophysics and spectroscopy, that endings are not always as final as they appear. That some things survive what should destroy them. That survival is possible even when the event was genuinely catastrophic and the damage was genuinely severe. Whether this is comforting or disturbing depends, perhaps, on where you sit with endings. On whether you prefer the clean finality of complete destruction to the complicated persistence of something that has survived but is permanently changed. But the universe does not ask for our preference. The universe simply does what the physics allows. And what the physics allows, it turns out, includes zombie stars. Includes things that partially die and continue on. Includes the complicated middle ground between the ending and the going on that we never had a name for before. Includes the complicated middle ground between the ending and the going on that we never had a name for before, and that we are still, as a field and as a species, working to fully understand. What this means for death itself, for the concept of death as a physical process in the universe, is that the concept requires revision. Not abandonment, not replacement, but genuine revision. An acknowledgement that death, even in the relatively clean domain of stellar astrophysics where we thought we had it well defined, turns out to be messier than we expected, more variable, more open to exceptions. The universe breaks its own rules. Not often, not arbitrarily, but sometimes, in specific circumstances, under specific conditions, the outcome is not what the rules predict. And in those circumstances, something comes into existence that the rules did not provide for. Something that lives in the space between the expected categories. Something undead. And understanding the undead, in astrophysics as in folklore, requires us to revise our understanding of both life and death simultaneously. Because the undead is defined by its relationship to both. It is not alive in the way it was alive before. And it is not dead in the way the rules said it should be dead. It occupies a third state, a state that the binary framework of life and death cannot accommodate. The zombie star is this third state, rendered in the language of nuclear astrophysics. And the galaxy, it turns out, is populated with them. Drifting through the dark in numbers we are only beginning to estimate. Each one a testament to the universe's willingness to violate its own expectations. Each one a reminder that death, even at the stellar scale, is not always what it appears. When LP40365 was identified and confirmed, the question that immediately followed in the minds of the astronomers who had found it was not only what is this, but how many others are there? When LP40365 was identified and confirmed, the question that immediately followed in the minds of the astronomers who had found it was not only what is this, but how many others are there? A single example of anything in the universe is interesting, But a single example is also, potentially, an anomaly, a fluke, a rare alignment of circumstances so unusual that it may never repeat. A population of examples is something different entirely. A population tells you not only that the thing can happen, but that it does happen regularly as part of the normal ongoing business of the universe. So the question became, is LP40365 an anomaly, or is it the first identified member of a population? The theoretical models, the same models that had predicted the existence of zombie stars before any were observationally confirmed, suggested strongly that LP40365 was not alone. If Type Iax supernovae occur, and they do, they have been observed, then zombie stars must be produced whenever a Type Iax event leaves behind a surviving remnant. And the models suggested that most Type Iax events do leave a surviving remnant. Not all of them. The details of the deflagration process are variable enough that in some cases the explosion might be energetic enough to completely unbind the white dwarf. But in many cases, perhaps in the majority of cases, something survives. This means that every Type Iax supernova in the history of the galaxy that was energetically insufficient to completely destroy its white dwarf has created a zombie star. And the galaxy is old. The Milky Way has been forming stars and hosting binary systems and producing white dwarfs for over 10 billion years. The number of Type Iax events that have occurred in the galaxy over that time, and the number of zombie stars that those events have created, is not trivially small. The number of Type Iax events that have occurred in the galaxy over that time, and the number of zombie stars that those events have created, is not trivially small. Estimates vary because the rate of Type Iax supernovae relative to Type I supernovae is itself an uncertain quantity. Type I supernovae are observed in external galaxies and in the historical record of our own galaxy, and their rate is reasonably well constrained. Type Iax events are less luminous, more difficult to detect, and the historical record is incomplete. But current estimates suggest that Type Iax events occur at perhaps 1/3 to 1/2 the rate of Type I events. If 1 in 3 supernovae of this class is of the Iax variety, and if most Iax events produce a surviving remnant, then the galaxy should contain a significant population of zombie stars. How significant? The numbers that emerge from the models are striking. Some estimates suggest that the Milky Way could contain anywhere from 100 million to perhaps 1 billion zombie stars. 100 million to 1 billion stellar ghosts, drifting through the galaxy, cooling and dimming over billions of years, their extraordinary velocities gradually being moderated by the gravitational potential of the galaxy as they travel through it. 100 million to 1 billion. These are numbers so large that they transform the zombie star from an exotic curiosity into something almost commonplace, at least in the statistical sense. Not visible, not easily detectable, but present throughout the galaxy, dispersed through its volume by the kicks they received at birth and the billions of years of subsequent travel. Why have we not found more of them? The answer is several-fold, and each part of it reveals something interesting about both the objects themselves and the limitations of our ability to survey the galaxy. The answer is several-fold, and each part of it reveals something interesting about both the objects themselves and the limitations of our ability to survey the galaxy. The first reason is that zombie stars are faint. Even a freshly formed zombie star, hot and inflated in the immediate aftermath of the explosion, is not a spectacular object by the standards of the night sky. It is a compact object, hot but small, and its total luminosity is modest compared to normal stars. As it cools over millions and billions of years, it becomes fainter still. The oldest zombie stars, the ones created in the early history of the galaxy, have had billions of years to cool, and they may by now be so faint that they are essentially invisible to current survey programs. The second reason is that zombie stars emit much of their radiation in the ultraviolet. We have already touched on this. The wavelengths where these objects shine most brightly are not the wavelengths that ground-based telescopes can easily access. Space-based ultraviolet telescopes are the natural tools for finding zombie stars, and while such telescopes exist, their survey coverage of the sky is not complete. There are vast swaths of the galaxy that have not been examined with the ultraviolet sensitivity needed to detect these objects. The third reason is that zombie stars look unusual but not dramatically obvious. LP40365 had been cataloged for decades before anyone recognized what it was. It required not only the measurement of its spectrum and its velocity, but also the theoretical framework of zombie stars to interpret those measurements correctly. Without the theoretical prediction, the unusual composition and extraordinary velocity of LP40365 might have remained unexplained indefinitely, or explained incorrectly, attributed to some other mechanism that produced similar observational signatures. This last point is particularly important. It suggests that the galaxy may be full of objects like LP4365 that are sitting in existing catalogs, already measured, already characterized, waiting for someone to recognize them for what they are. The data may already exist. The zombie stars may already have been found, in the sense that their light has already been collected and recorded. They simply have not been identified yet, because the process of recognition requires both the data and the interpretive framework. Several candidate zombie stars have been proposed in the years since the identification of LP4365. Objects with unusual compositions that show signatures of partially burned nuclear material. Objects with high peculiar velocities that require an explosive event for explanation. Objects that sit in the right region of the temperature-luminosity diagram for a cooling zombie star remnant. None of these candidates are as well characterized or as confidently identified as LP4365, but the pattern they form suggests that the population is real and that the survey of it is just beginning. None of these candidates are as well characterized or as confidently identified as LP4365, but the pattern they form suggests that the population is real and that the survey of it is just beginning. There is also a specific category of objects that may be related to zombie stars, but occupy a slightly different niche. These are the hypervelocity white dwarfs, compact objects moving at extreme velocities that could have been accelerated not by the classic zombie star mechanism of a partial explosion, but by the ejection of the companion star in the aftermath of a complete Type Iax supernova. When a white dwarf in a binary system undergoes a complete Type Iax explosion, its companion star is suddenly released from the gravitational anchor of the binary. It is no longer in orbit around the white dwarf. It is free, and it is moving, and the velocity it had during its orbital motion now carries it in a straight line through space at high speed. These companion star survivors of complete Type Iax supernovae are called runaway stars, or sometimes donor stars, because they donated mass to the white dwarf that eventually exploded. And they provide a complementary perspective on the binary star death events that produce both Type Ia and Type Iax supernovae. When you find a runaway star, you are finding evidence of a complete explosion. When you find a zombie star, you are finding evidence of an incomplete one. Together, they are the survivors of two different versions of the same kind of event. Together, they are the survivors of two different versions of the same kind of event. The galaxy is thus populated with two distinct kinds of ghosts. The companion survivors of complete explosions, moving at high velocity but otherwise structurally normal, stars that were witnesses to a catastrophe and bear no physical marks of it beyond their anomalous speed. and the zombie stars, the remnants of incomplete explosions, moving at high velocity and bearing in every atom of their peculiar compositions the undeniable evidence of having been the direct target of the catastrophe they survived. Both kinds of ghosts are real. Both have been found. Both are, right now, drifting through the galaxy in numbers that our current surveys have barely begun to count. And both kinds of ghosts are, in their different ways, telling the same story. The story of a universe that does not always follow its own rules, that does not always deliver the clean and total destruction that the physics is supposed to prescribe, that sometimes leaves survivors, sometimes leaves things behind that should not be there, sometimes allows the incomplete and the ambiguous to persist alongside the clean and the final. The galaxy is more haunted than we knew. The galaxy is more haunted than we knew. And the haunting is not metaphorical. It is not a literary image or a poetic interpretation. It is a physical fact supported by spectroscopic measurements and velocity analyses and theoretical models confirmed by observation. The ghosts of the galaxy are real. They are measurable. They are drifting through the space between the stars right now, cooling degree by degree toward the eventual cold darkness that is the final destination of everything. But even that final darkness is a long way off for most of them. Billions of years of cooling remain. Billions of years of drifting through the galaxy, passing through star-forming regions and empty voids, crossing spiral arms and traversing the halo. The zombie stars have time, enormous quantities of time, the same patient, geological, astronomical time that characterizes all the large-scale processes of the universe. They are in no hurry. They were not in a hurry to be created, forming only after billions of years of binary star evolution set the conditions for their impossible survival. And they are not in a hurry to disappear, fading on timescales that dwarf the entire history of human civilization by factors too large to hold in the mind comfortably. And they are not in a hurry to disappear, fading on timescales that dwarf the entire history of human civilization by factors too large to hold in the mind comfortably. The galaxy's ghosts drift on. The count of them grows as the survey programs improve. The models are refined with each new identification, each new measurement, each new piece of data that tells us something more about the population of stellar survivors that the universe has been quietly accumulating throughout its history. The haunting is ongoing, and it will continue long after every living thing that currently exists in this galaxy has been born and lived and died, and the stars that currently shine have burned down to their own quiet remnants, and the galaxy itself has aged beyond easy recognition. The zombie stars will still be there. Dimmer, colder, harder to find. But there, drifting in the dark. Drifting in the dark. Step back now. Step back far enough that the individual objects, the specific zombie stars, and their companion survivors, and the named examples like LP 4365 become too small to see. Step back far enough that the Milky Way itself comes into view, not as the hazy band of light across the night sky, but as the structure it actually is, a barred spiral 100,000 light-years across, containing several 100 billion stars, arranged in arms and a central bulge and a halo that extends far beyond the visible disk. Hold this picture. The galaxy seen whole. Now begin to populate it. Not with the living stars, the ones that are currently fusing hydrogen in their cores, burning through their fuel at the steady and predictable rates that determine their lifetimes. Not with the young blue giants that will live for only a few million years and then explode in core collapse supernovae. Not with the middle-aged yellow dwarfs like our own sun, quietly proceeding through their billions of years of hydrogen burning. Populated instead with the dead. Populated instead with the dead. Every star that has ever died in this galaxy has left something behind. Not always something visible, not always something detectable with current instruments, but something. The universe does not erase. It transforms, and the products of stellar death are scattered throughout the volume of the galaxy in numbers that, when you begin to add them up, are genuinely staggering. There are neutron stars, the collapsed remnants of massive stars that ended their lives in core collapse supernovae, dense spheres of neutronium, typically about 20 kilometers in diameter, containing roughly 1.5 solar masses. Spinning, in many cases, at hundreds of rotations per second, emitting beams of radio waves and X-rays and gamma rays that sweep through space like the beams of cosmic lighthouses. The Milky Way is estimated to contain roughly 1 billion neutron stars, 1 billion dense, rapidly spinning remnants of stellar deaths, distributed throughout the galactic volume. Most of them are invisible, their beams not directed toward any detector, their radiation too faint or too diffuse to be detected at any significant distance. But they are there. There are black holes, the remnants of the most massive stars, objects whose gravity is so extreme that not even light can escape. Black holes of stellar mass, formed in the depths of the heaviest stars, are estimated to number in the hundreds of millions in the Milky Way. Again, mostly invisible, mostly undetectable, making their presence known only when they happen to be in a binary system with another star that they can accrete material from, or when they happen to pass close to something that reveals their gravitational influence. But they are there. Hundreds of millions of regions of space-time from which nothing escapes, distributed throughout the volume of the galaxy, invisible and patient and permanent. Hundreds of millions of regions of space-time from which nothing escapes, distributed throughout the volume of the galaxy, invisible and patient and permanent. There are white dwarfs, the cooling remnants of the smaller stars, objects like the Sun and below, that ended their lives by shedding their outer layers and leaving behind their dense, degenerate cores. The Milky Way is estimated to contain roughly 10 billion white dwarfs, 10 billion cooling embers, ranging from the newly formed and still intensely hot to the ancient and nearly cold, distributed throughout the galactic disk and halo. Most of them are too faint to be detected at significant distances. Most of them are invisible against the crowded stellar background. But they are there, in their billions, slowly and patiently cooling toward the eventual cold darkness that is the final destination of every white dwarf that is left alone long enough. And then there are the zombie stars. And then there are the zombie stars. Add them to the picture. 100 million, perhaps more, drifting through the galactic volume, moving faster than the average stellar velocity because of the kicks they receive from their partial explosions, carrying their unusual compositions and their undead light and their extraordinary velocities through a galaxy that is already populated with 1 billion neutron stars and hundreds of millions of black holes and 10 billion white dwarfs. The galaxy, when you populate it with all of its dead and its dying and its impossible survivors, begins to look less like a collection of bright lights in the dark and more like something else entirely. It begins to look like a graveyard. Not a neat graveyard. Not the kind with orderly rows and legible inscriptions and a clear separation between the living and the dead, but the other kind. The ancient kind. The kind where the graves are scattered across an enormous landscape without obvious pattern, where the markers have long since faded or been lost, where the living and the dead exist in the same space, without any clear boundary between the territory of one and the territory of the other. The Milky Way is this kind of graveyard. Its volume is shared between the living stars, still burning, still fusing, still radiating the light that makes the galaxy visible from outside, and the dead and the undead, the neutron stars and black holes and white dwarfs and zombie stars that are scattered throughout the same space, invisible or nearly invisible, moving through the same regions, occupying the same spiral arms and halo and disk. Every star you can see in the night sky is accompanied, in the statistical sense, by many things you cannot see. By the dead stars that formed before it and ended their lives in its vicinity. By the white dwarfs cooling in nearby orbits. By the neutron stars spinning in the dark. By the black holes that warp the space-time through which the visible star moves. The night sky, for all its appearance of simple brightness against simple darkness, is in reality a densely layered landscape of the living and the dead, the burning and the cooled, the normal and the monstrous. The zombie stars are part of this landscape. They are part of the graveyard, but they occupy a special position within it because they are the most ambiguous of all the dead. A neutron star is clearly dead. A black hole is clearly dead. A white dwarf is clearly dying. But a zombie star is something that resists classification by the normal framework of stellar death entirely. A neutron star is clearly dead. A black hole is clearly dead. A white dwarf is clearly dying. But a zombie star is something that resists classification by the normal framework of stellar death entirely. It is not alive. It is not generating energy through fusion. It is not doing the thing that defined it as a white dwarf, which was cooling toward the eventual darkness. It is doing something else, something that the categories of stellar death did not predict, cooling in a different way, from a different starting point, with a different composition and a different temperature profile and a different velocity and a different set of problems related to its disrupted internal structure. It is the graveyard's most disturbing inhabitant, not the most dangerous, not the most energetic, but the most philosophically troubling, the one that refuses to stay in its assigned category, the one that crossed the threshold that should have ended it and came back. In every culture that has ever built a graveyard, there has been anxiety about the boundaries, about the possibility that the dead might not stay in their proper territory, about the liminal space between the living and the dead and what might inhabit it. These anxieties are as old as human culture itself. They manifest in folklore and religion and literature, in the stories of the undead that every culture seems to produce independently. The zombie star is the universe's version of this anxiety, made physical. The zombie star is the universe's version of this anxiety, made physical. It is the inhabitant of the liminal space, the thing that crossed the boundary between the living and the dead and refused to settle on one side of it. It exists in the graveyard, but is not quite of it. It occupies the space of the dead, but carries the heat of something that has not yet fully completed the process of dying. And the galaxy, the graveyard in which it drifts, does not distinguish between it and its more conventionally dead neighbors. The neutron stars and the zombie stars and the black holes and the white dwarfs and the living stars occupy the same space, follow the same galactic gravitational potential, move through the same spiral arms and voids. The graveyard does not organize its inhabitants by category. It simply contains them all, the normal dead and the conventionally dying and the impossibly undead, distributed through its enormous volume in whatever proportions the history of stellar evolution has produced. And above your head right now, this graveyard is turning. The Milky Way rotates, slowly, the solar system completing one orbit of the galactic center roughly every 230 million years. And as it rotates, all of its inhabitants rotate with it, the living and the dead and the undead, wheeling through the dark in their billions. The stars you can see from where you are lying are the bright surface of a much deeper landscape. Behind them, and between them, and in every direction you cannot easily comprehend, the graveyard extends. Billions of dead things and dying things and things that refuse death. all moving through the same vast dark, all subject to the same physics, all part of the same galaxy that has been accumulating its dead for 10 billion years and will continue to do so for billions more. The night sky is a graveyard roof. The night sky is a graveyard roof. What you see when you look up is the inside surface of a structure that extends far deeper than the light allows you to see. And somewhere in that depth, the zombie stars drift. Silent, cooling, marked alone. Part of the graveyard, and not quite part of it. Both things simultaneously, as the undead always are. Let us stay with the darkness for a while. Not because the story requires us to, not because there is more data to present or more theoretical framework to establish, but because the darkness deserves to be inhabited for longer than a passing moment. Because there is something in what we have been describing tonight that resists being processed too quickly, that wants to be sat with, that has a weight and a texture that only become fully apparent when you stop moving through the material and simply rest in it for a time. The horror of survival. This phrase deserves unpacking. Because survival, in most contexts, is not associated with horror. Survival is the good outcome. Survival is what we root for, what we work for, what we celebrate when it is achieved against difficult odds. The story of survival is almost always a story of triumph, or at least of relief. The thing that survived is better off than the thing that did not. Survival is positive. The story of survival is almost always a story of triumph, or at least of relief. The thing that survived is better off than the thing that did not. Survival is positive. And yet there is a category of survival that carries a different quality. A category that is not triumph or relief, but something closer to the uncanny. Something that belongs to the space where survival and horror become difficult to distinguish from each other. Think of what a zombie star has been through. It began as a white dwarf, a dense, cooling remnant of a star that had lived its life honestly, burned its hydrogen through billions of years of patient fusion, shed its outer layers in the normal course of stellar death, and settled into the long, cooling sequence that should have been its final chapter. A white dwarf is not glamorous. It is not spectacular, but it has a kind of dignified quiet to it, the quiet of a thing that has finished its work and is now simply resting, radiating the last of its stored heat into the cold of space. And then the companion came. And the companion, through the patient and relentless mechanism of mass transfer, began to feed the white dwarf material, began to push its mass upward, degree by degree, toward the limit that should have ended it cleanly. And the white dwarf, receiving this material, began its approach toward the moment of its own destruction, a destruction that, had everything gone according to the expected pattern, would have been instantaneous and complete. A thermonuclear detonation so thorough that no trace of the white dwarf's identity would have survived. But the detonation was not complete. The thermonuclear flame that ignited in the core did not propagate to the edge. It burned partway through, deposited its energy, flung the outer layers into space, and then stalled. And what was left behind was the core, the inner regions, the part of the white dwarf that the explosion did not reach. Not intact, not unaffected, but there. This thing that was left behind, this zombie star, has been through something that we do not have a good human analogy for. It has been through the beginning of its own total annihilation. It has experienced the ignition of the event that should have erased it. It has felt the thermonuclear flame approaching its innermost regions and then stopping, impossibly, just short of completion. And now it exists in the aftermath of that experience. The horror of this survival is not in the drama of the moment. The moment itself is over. It happened thousands of years ago or millions of years ago, depending on which zombie star we are considering. The acute violence of the event is long past. The horror is in the persistence, In the continuing existence of this scarred and altered thing in the aftermath of what should have been its final moment. The horror is in the persistence. In the continuing existence of this scarred and altered thing in the aftermath of what should have been its final moment. A zombie star carries its history physically, not in memory, not in any experiential sense, but in the atoms of its atmosphere and the altered structure of its interior and the unnatural velocity of its trajectory through space. Every measurement of a zombie star is a measurement of the event that tried to destroy it. Every spectral signature of the unusual elements in its atmosphere is a record of the incomplete burning. Every anomalous absorption feature in its spectrum is a fingerprint of the catastrophe survived. The horror of survival, in this context, is the horror of being permanently defined by the thing that almost killed you, of being made into something new and strange by the experience, without any possibility of return to what you were before. The zombie star cannot unexperience the Type Iax supernova. It cannot shed the unusual composition it was given by the partial burning. It cannot restore the identity it had as a normal white dwarf, cooling quietly in a binary system. What it was before the explosion is gone, and what it is now is defined entirely by the explosion, by the failure of the destruction, by the surviving of the unsurvivable. There is a weight to this that transcends the astrophysics. There is something in the image of a thing permanently altered by a catastrophe it should not have survived, drifting through the vast dark of the galaxy with the marks of that catastrophe on every surface, that resonates with something in the human experience. Not because stars are conscious, or because zombie stars feel anything, or because the experience of a stellar object maps onto human experience in any literal sense. Not because stars are conscious, or because zombie stars feel anything, or because the experience of a stellar object maps onto human experience in any literal sense, but because the archetype of the survivor marked by the catastrophe that almost destroyed them is one of the oldest and most resonant themes in human storytelling. We recognize something in the zombie star, something that the Gothic tradition has been articulating for centuries in its explorations of the undead, in its meditations on what it means to persist beyond the moment that should have been the ending. The zombie star is the universe's own contribution to this tradition, enacted in the medium of plasma physics and nuclear astrophysics rather than in the medium of literature and mythology. But the resonance is real. And there is a specific quality to the zombie star situation that goes beyond even the ordinary horror of marked survival. Because the zombie star is alone. When the Type Iax supernova occurred, the binary system that produced it was destroyed. The companion star, which had been orbiting the white dwarf for millions of years, transferring mass across the gravitational bridge between them, sustaining the conditions that led to the explosion, was released from the binary. It was struck by the blast wave of the explosion. It may have survived, as we discussed in the context of runaway stars, but it was flung away at high speed, no longer bound to the zombie star, no longer in any gravitational relationship with it. The zombie star was alone from the moment it emerged from the explosion. No companion, no binary system, no gravitational anchor, just the kick velocity from the asymmetric ejecta and the infinite cold dark of the galaxy in all directions and billions of years of drifting ahead. Just the kick velocity from the asymmetric ejecta and the infinite cold dark of the galaxy in all directions and billions of years of drifting ahead. This solitude is a physical fact. It is not a projection of human emotion onto a stellar object, but the image of it, the image of this scarred and altered thing moving through space with no companion and no destination, defined entirely by the catastrophe that created it, is a deeply Gothic one. In the literature of the undead, the wandering is often the punishment. The thing that cannot die is also the thing that cannot rest, the thing that is condemned to move through the world without belonging to it, without the normal relationships and anchors that give existence its context. The zombie star enacts this pattern with perfect fidelity, not because the universe is telling a story, but because the physics of an asymmetric explosion produces exactly this outcome. A survivor, alone, moving, marked, and the marks will never fade. This is the deepest horror. The composition of a zombie star's atmosphere, the unusual elements deposited by the partial burning, will persist for the entire cooling lifetime of the object. Billions of years from now, if something with instruments sensitive enough to measure it should encounter LP 40365 or any other zombie star, the spectral signatures of the Type Iax supernova will still be there, still readable, still telling the story of the event that created this thing that should not be. The scar is permanent. The horror of survival does not diminish with time. It is written into the object's very composition in a way that cannot be erased by cooling or contraction or any of the normal processes of stellar evolution. The scar is permanent. The horror of survival does not diminish with time. It is written into the object's very composition in a way that cannot be erased by cooling or contraction or any of the normal processes of stellar evolution. The zombie star is, for all practical purposes of observation, permanently identifiable as what it is: a survivor, a mutilated remnant, an object that carries its impossible history in every atom. There is a term in astronomy for the chemical signatures of nuclear events preserved in stellar atmospheres. The term is nucleosynthesis products. The products of nuclear burning, the heavier elements created in the thermonuclear reactions of the partial explosion, mixed into the atmosphere of the zombie star and detectable by spectroscopy. It is a clinical term, a technical term, a term that does nothing to communicate the strangeness of what it is describing. What it is describing is a permanent record of attempted annihilation. A set of fingerprints left by a fire that burned partway through a living star and then stopped. A chemical autobiography of survival against the odds. Every zombie star is writing this autobiography, not in words or in symbols, but in the composition of its atmosphere, in the wavelengths of light it absorbs and emits, in the data that eventually reaches a telescope somewhere and is decoded by an instrument into numbers that a mind can interpret. The horror of survival is the horror of the story that cannot be left behind, of the thing that defines you being also the thing that you cannot separate from, of being permanently the survivor of the event rather than simply the thing that continues to exist after the event. The zombie star is not simply a star that has been through something terrible. It is a star that has been remade by the terrible thing. It is a star that has been remade by the terrible thing. It is a star whose entire present existence is a consequence of and a monument to the catastrophe. Without the catastrophe, there would be no zombie star. The thing that almost destroyed it is also the thing that created it in its current form. The violence and the survival are not separable. The horror and the persistence are not separable. This is the deepest thing about the zombie star. Not its unusual composition or its extreme velocity or its undead light or any of the specific measurable properties that allow astronomers to identify it, but this fundamental inseparability of the catastrophe from the continuation. The zombie star is what it is because of what happened to it, and what happened to it was the thing that should have ended it entirely. The horror of survival, at its deepest level, is the horror of being made into something new by the very event that was supposed to unmake you. And the zombie star drifts on, through the cold and the dark and the billions of years, unmourned and unwitnessed and unremarked by the universe that produced it, carrying its impossible history in every atom. A mutilated core of something that refused to die. An eternal, wandering reminder of a catastrophe that never quite completed its work. And the galaxy continues around it, indifferent, vast, full of its own ongoing processes of birth and death, and everything in between, including the strange and haunting in-between that the zombie star inhabits. The horror is real, and it drifts on. Before we rest, before we let the night do its final work and let the story settle into something that the sleeping mind can hold without effort, there is one more thing worth sitting with. One more layer to the zombie star story that we have not yet fully opened. It is about scars. It is about scars, not metaphorical ones, not the psychological scars of human experience, though we will circle close to those before we are done, but physical scars. Real ones. The actual, measurable, spectroscopically detectable alterations in the composition of a zombie star's atmosphere that record the event of its survival. Scars, in the human sense, are a form of memory written on the body. They are the body's record of a wound, a place where damage occurred and healing followed, and the healed tissue, though functional, is different from the undamaged tissue around it. Denser, sometimes, less flexible, a different color or texture. And the scar does not fade with time the way a bruise fades or a cut closes. It persists. It is a permanent alteration, a lasting inscription in the body's surface that says, here, something happened. Here, there was damage. Here, the body was broken and repaired, and the repair is visible. The zombie star scars are not tissue. They are nuclear. They are written not in the density of healed skin, but in the relative abundances of atomic nuclei in the white dwarf's atmosphere. In the specific proportions of oxygen to neon to magnesium, in the presence of elements that should not be there in those quantities, in the absence of elements that should be there but are not. Nuclear scars. The fingerprints of a thermonuclear fire that burned partway through a star and then stopped. When astrophysicists analyze the spectrum of LP 40365, what they are reading, in the language of spectral lines and absorption features, is a record of a specific sequence of nuclear reactions that occurred in the interior of a white dwarf thousands of years ago. The oxygen that appears so prominently in the spectrum was created, at least in part, by the burning of carbon in the runaway thermonuclear deflagration. The oxygen that appears so prominently in the spectrum was created, at least in part, by the burning of carbon in the runaway thermonuclear deflagration. The neon is a product of oxygen burning at the extreme temperatures reached in the most energetic parts of the flame. The magnesium tells of conditions even more extreme, pressures and temperatures that were reached only fleetingly in the hottest and most violent moments of the incomplete explosion. Each element in the spectrum is a sentence in a story. Each absorption line is a word in a language that describes, to those who can read it, the physical history of the catastrophe. The spectrum of a zombie star is an autobiography, written not in prose but in photons, not on paper but in the wavelengths of light that the star absorbs as it radiates into space. And the autobiography does not fade. This is the key point. This is the thing about scars, about both the biological kind and the nuclear kind, that gives them their particular weight. A memory can fade. The emotional and cognitive record of a difficult experience is subject to the normal processes of time and neurological change, and the gradual rewriting that memory performs on itself. Human memories are unreliable, malleable, subject to revision. They can be lost entirely. The experience remains, in some philosophical sense, having happened, but the record of it in the mind that experienced it can be erased or distorted beyond recovery. A scar cannot fade in this way. A scar is not a record in a medium that can be overwritten. It is a physical alteration in the matter itself. The healed tissue is not going to become unhealed tissue again. The scar is there, permanent, as long as the body is there. The nuclear scars of a zombie star are the same. The nuclear scars of a zombie star are the same. The oxygen and neon and magnesium in LP 40,365's atmosphere are not going to become carbon and oxygen again. The nuclear reactions that produce them cannot be reversed. The thermonuclear fire that burned through the interior of the white dwarf, converting its material into the products of nuclear burning, did something to the matter that cannot be undone. The matter has been changed permanently at the level of atomic nuclei, and that change is written into every measurement that can be made of the object spectrum. The zombie star cannot forget what happened to it, not because it has a memory, but because forgetting, in this context, would require the matter itself to unremember, would require the nuclear reactions to run backward, the oxygen to become carbon again, the scars to unheal. And the laws of thermodynamics, the deep rules about the direction of time and the irreversibility of certain physical processes forbid this. The zombie star is permanently scarred by its survival. And the permanence is not a tragedy, though it might initially feel like one. It is simply a property of the physics, a consequence of the irreversibility built into thermonuclear reactions and the second law of thermodynamics. The scar is the price of surviving, the price of being the object at the center of an explosion that should have been total and was not. But there is another way to read the scars. Not as damage, not as evidence of something that was done to the zombie star, but as evidence of something that the zombie star endured, of a history that the object carries, of a depth of experience, if we can use that word loosely, that no ordinary white dwarf possesses. An unscarred white dwarf is cooling from its initial temperature. An unscarred white dwarf is cooling from its initial temperature. It is the remnant of a star that lived its life and died in the normal way and left this dense, cooling sphere behind. It carries no record of anything unusual. Its spectrum is the spectrum of a cooling, degenerate object, unremarkable by the standards of the white dwarf population. It has a past, of course. Everything has a past. But the past of an ordinary white dwarf is a quiet one, a normal one, a past that fits into the standard categories without difficulty. The zombie star's past is not quiet. Its past is the most violent event that a white dwarf can experience, the ignition of the thermonuclear fire that was supposed to destroy it entirely. And the record of that past is written in the scars, in the oxygen and the neon and the magnesium, in the composition that does not fit any ordinary category, in the spectrum that says, to anyone who reads it, this object has been through something. The language of scars is the language of history. It is the universe's way of preserving a record of events that would otherwise leave no trace. If the Type Iax supernova that created LP 40365 had been a complete detonation, if the white dwarf had been fully destroyed, there would be no record of that specific event in any surviving object. There would be an expanding cloud of debris, a fading supernova remnant, a region of space that was once occupied by a binary system and is now occupied by spreading ejecta. But there would be no object bearing the marks of the event in its composition. There would be no scar. The zombie star is the scar. It is the surviving record of an event that, in its complete form, would have left no record. By surviving, it preserves the history of its own near destruction. By existing, it says, this happened, here, to this object, and the object is still here to tell you. This is the deepest truth about the language of scars. They preserve history that would otherwise be lost. They make legible the events that shaped the objects that bear them. They turn the blank and uninformative surface of an unscarred object into a text that can be read. The zombie star is a text, a long and complex and physically encoded text written in the language of nuclear reactions and spectral lines that says, In the most literal physical sense possible, I was here. I went through this, and I am still here. There is something in that language, in the language of scars and survival, and the permanence of physical alteration that resonates beyond astrophysics. Because scars, in the human sense, carry their own version of this dual quality. They are simultaneously evidence of damage and evidence of survival. They mark the place where something was broken, and also the place where something healed, or at least continued, beyond the breaking. To carry a scar is to carry a history. It is to be permanently in relationship with an event that happened in your past, to have the event written on your body in a language that anyone who looks closely enough can read. It is to be, in some sense, defined by what you endured. Not entirely, not only, but to have the endurance present in your surface, inscribed in matter, legible to those who know the language. The zombie star knows this language. Not consciously, not experientially, but physically. It carries its history in its composition in the way that a scarred person carries their history in their skin. The language is different. The medium is different. The scale is unimaginably different. But the principle is the same. The event that marked you is also the event that proved you could endure it. The scar is simultaneously the record of the wound and the evidence of the survival. And the zombie star, drifting through the dark with its nuclear scars and its undead light and its extraordinary velocity, is the universe's own version of this truth. A thing that was marked by the unsurvivable, a thing that carries the marking permanently in every atom of its altered composition. A thing whose entire present existence is inseparable from the event that tried to end it and failed. The language of scars is not easy to read. It requires instruments and theoretical frameworks and the patience to sit with data until it resolves into meaning. But the meaning, when it comes, is precise and deep and undeniable. This happened. This object endured it. And the endurance is written here, in this spectrum, in these absorption lines, in this composition that does not fit any ordinary category. Read it slowly. It took a long time to write. Read it slowly. It took a long time to write. It took the accumulation of mass over millions of years and the crossing of the Chandrasekhar limit and the ignition of the thermonuclear fire and the propagation of the deflagration and its eventual stalling and the survival of the core and the billions of years of subsequent drift. All of that is in the spectrum. All of that is in the scar. And now, finally, there is a mind that can read it. The zombie star has been drifting through the galaxy for thousands of years, writing its autobiography in the language of light that no one knew how to read. And now there are instruments and theoretical frameworks and the long patient work of science that has built them, and the autobiography can be decoded. The star has been waiting for a reader. And we are here, reading the language of scars by the light of the stars above us and the silence of the night around us, and the deep and patient mystery of a universe that preserves its history in the matter of its survivors. Rest now with this. With the knowledge that history is written in matter, that survival is written in scars, that the zombie star's impossible existence is the universe's own record of a rule that was broken and a death that did not quite take. Rest with the language of scars. It is a language that tells the truth. And the truth, strange and dark and beautiful as it is enough. The night has deepened now. The night has deepened now. Not just the physical night, though that is here too, the darkness that surrounds you, the quiet that has settled over everything, the particular quality of the air in the small hours when the world has finally finished its business for the day and let itself be still. But the other kind of night as well, the one that we have been walking through together for the length of this story, the darkness that lives at the edge of understanding, where the familiar maps run out and the territory becomes something that the maps were never designed to represent. We have been in that darkness together. We have walked through the life and death of stars. We have stood at the edge of the white dwarf's long, cooling sequence and felt the weight of the process that leads, slowly and inevitably, toward the moment of ignition. We have watched the thermonuclear flame ignite in the carbon-oxygen interior and fail, impossibly, to complete its work. We have found LP-40365, drifting through the galaxy 1,000 light-years away, glowing with its undead light, carrying in its peculiar spectrum the indelible record of a catastrophe survived. We have sat with the horror of survival, with the permanent marking, with the solitude of the thing that came through the unsurvivable and emerged on the other side. And now, at the end of all of that, I want to invite you to do something that might seem, at first, like a strange response to everything we have described. I want to invite you to rest. Not despite the zombie stars, not in ignorance of them or in denial of what they represent, but with them, beneath the same sky that contains them. Beneath the same sky that contains them. As a conscious and temporary and fragile thing that shares a galaxy with these impossible survivors. Because here is what the story of the zombie stars tells us. When we step back from the gothic details and the astrophysical specifics and the philosophical implications, and ask simply, what is the deepest truth here? The deepest truth is that the universe is stranger and more complex and more various than any model we have ever built to describe it. That the rules we extract from the universe are real rules, true in the enormous majority of cases, accurate descriptions of how things actually work. But that the universe is not bound by our rules in the way that we are sometimes tempted to believe. It is not constrained by the elegance of our models or the convenience of our categories. It produces, with what seems like a casual indifference to the theoretical expectations of the minds that have emerged within it, things that those expectations did not predict and cannot fully account for. Things like zombie stars. Things like stellar corpses that refuse the grave, that drift through the dark with their undead light, that carry their impossible histories in their altered compositions, that exist as permanent reminders that the universe's categories are always provisional. And this strangeness, this complexity, this refusal of the universe to be quite what we expected is not a threat. It is an invitation. It is the universe extending toward us, again and again, the invitation to look more carefully, to revise our models, to hold our certainties a little more lightly, to remain open to the possibility that what we find next will not be what we expected. Every zombie star that is discovered is the universe saying, there is more here than you knew. Every unusual spectrum, every anomalous velocity, every object that does not fit neatly into the existing categories, is an invitation to expand the categories, to deepen the understanding, to recognize that the picture is always more complex than the current best model suggests. This is not a source of anxiety. Or rather, it need not be, even though it can feel like one when you are standing at the edge of what is understood and looking out into the territory that is not yet mapped. It can instead be a source of something closer to wonder, of the specific, quiet, deep wonder that comes from recognizing that you are in the presence of something that exceeds your understanding, not threatening you, not requiring anything from you, just being larger than what you knew. The zombie stars are not threats. They drift through the galaxy hundreds or thousands of light years away, cooling slowly, posing no danger to anything. They are simply there. They are simply what they are. Objects whose existence required a revision of our models of stellar death, whose discovery expanded the range of what we know the universe is capable of. And knowing they are there, knowing the sky above us contains these drifting, cooling, haunted things, does not make the sky more frightening. It makes it richer, more various, more fully inhabited by the strangeness that has always been its most honest characteristic. Think about what it means to lie beneath a sky that contains zombie stars. Not just normal stars, burning through their normal lives on normal timescales, following the expected paths of stellar evolution toward the expected ends, but also the others. The ones that went through the unsurvivable and survived. The ones that drift with their anomalous velocities and their unusual compositions and their undead light. The ones that broke the rules and continue to exist as evidence of the breaking. This sky is the actual sky. This is the sky above you right now, as you settle into the darkness and let the weight of the night rest on your shoulders. Not the simplified version, not the cleaned-up model with all the awkward exceptions removed, but the real one, complete with its zombie stars and its charred remnants and its stellar ghosts moving through the dark at speeds that flag them as survivors of something the physics said was unsurvivable. It is a stranger sky than most of us walk through our days remembering, but it is a more honest one, and there is a particular comfort, once you have let it settle in the honesty. In the recognition that the sky above you is not a simple backdrop, but a populated and complex and endlessly surprising landscape, full of things that are doing exactly what the physics requires of them, including occasionally doing things that the physics did not predict. The universe is not malevolent. It is not dark in the way that human darkness is dark, not purposefully obscure, not hiding things out of a desire to confuse or frighten. It is simply vast and complex and operating according to rules that took billions of years to produce minds capable of working them out, and that still regularly produce phenomena that those minds did not anticipate. It is the darkness of depth rather than the darkness of threat, the obscurity of richness rather than the obscurity of concealment. And the zombie stars, for all the gothic resonance of the image, for all the horror of survival that their existence implies, are ultimately part of this honest and rich and non-malevolent darkness. They are what happens when the physics allows an exception, when the conditions are right for a detonation that does not complete itself, when the rules are followed all the way to the edge of an outcome that the rules did not anticipate, and the universe, indifferent to the expectations of the astronomers who will eventually find the evidence, simply allows the outcome to stand. A white dwarf survives its own supernova. A zombie star comes into being, and the galaxy acquires another drifting, glowing, undead thing in its long catalog of strange and various objects. Rest with this. Let it be what it is, strange and dark and somehow, despite all of that, peaceful, because the universe is at peace with it. The universe does not experience the zombie stars as violations or as horrors. They are simply outcomes, simply objects, simply things that exist in the space they occupy and behave according to the physics of their current state. There is a specific kind of peace that comes from letting the universe be as strange as it is, from releasing the need for it to conform to the cleaner and simpler picture that our models describe, from accepting that the categories are always provisional, that the exceptions are always real, that the sky above us contains things we have not yet found, and things we have found but not yet understood, and things we understand only partially and imperfectly. This acceptance is not resignation. It is not the peace of giving up, of deciding that the strangeness is too great to engage with and withdrawing into comfortable ignorance. It is the peace of engagement, of having looked carefully at what is actually there and decided to find it beautiful, in all its complexity and all its darkness and all its refusal to be what the simple models said it should be. The zombie stars drift on. LP40365 moves through the galaxy right now, 1,000 light-years away in the direction of Lupus, at a speed that will eventually carry it beyond the gravitational boundary of the Milky Way entirely. It will leave the galaxy. It will become an intergalactic wanderer, one of the very few objects in the universe that has moved from inside a galaxy to outside it under the propulsion of its own failed death. And it will continue to drift and cool and dim long after everything that currently exists on this planet has run its course, long after the stars visible in tonight's sky have evolved through their remaining lifetimes, long after the galaxy it is leaving has changed beyond recognition. It does not know this. It experiences nothing of it. It is simply a physical object following the laws of physics with the complete and perfect indifference of all physical objects. But we know it. Lying here beneath the sky, aware of the dark and the stars and the vast machinery of the universe operating above us and around us and through us, we know that LP40365 is out there, drifting. That other zombie stars are drifting, unidentified, through other patches of the sky. The galaxy is populated with these impossible survivors, each one carrying its history in its altered composition, each one a testament to the universe's willingness to allow exceptions to its own most fundamental rules. And knowing this, we can rest. Not the rest of ignorance, not the rest of someone who does not know what is out there, but the rest of someone who knows and has sat with the knowing and has found that the knowing is not a burden but a gift. The gift of a sky that is more various and more complex and more honest than the simplified version. The gift of a universe that is stranger than expected and continues to surprise. The gift of zombie stars, of undead light, of charred remnants drifting through the dark, of mutilated cores glowing with the residual heat of their own impossible survival. This is the sky above you. This is the universe you live in, strange and dark and full of things that should not be and yet are, full of rules that are broken and exceptions that persist and survivors that carry their histories in their very atoms. And it is, for all of that, deeply and profoundly and inexhaustibly beautiful. The zombie stars drift on. The haunting continues. And you, lying beneath this sky, are part of the same universe that produced them, made of the same elements, forged in the same kinds of stellar fires, subject to the same physics, the same rules, and occasionally the same exceptions to those rules. Of looking up at the dark and knowing that the dark is not empty, that the universe is full of things that drift and cool and persist. Close your eyes. Let the undead sky hold you. And sleep.